Welcome back for another deep dive. Today we're going to really get into this paper about quantum diffusion and delocalization in one-dimensional band matrices.
Sounds pretty complex.
Oh, it is. But that's why we're here, to break it down and make it understandable.
Yeah, definitely interested to see how they use this flow method to prove their results.
Me too, and especially how they connect it to eigenvector delocalization.
Right, that connection is fascinating.
And, I think what's going to be particularly interesting is exploring that transition between random matrix and Poisson statistics.
Absolutely. That's a key aspect of understanding the behavior of these matrices.
So let's jump right in, shall we?
Let's do it.
All right. So page 1 starts off with the abstract and they get right to the point.
Yeah, they don't waste any time.
No, they don't. They highlight their main finding, which is that delocalization holds for bulk eigenvectors and quantum diffusion holds for the resolvent.
And this is specifically when the bandwidth is much larger than n raised to the power of 811.
Exactly. WN 811.
It's a mouthful, but it's at the core of their result.
Absolutely. Now, before we get too deep into the specifics,
Yeah.
it's helpful to step back and consider the historical context.
Right, because the authors do a great job of tracing the roots of random matrix theory all the way back to Wigner's work.
Oh, absolutely. Wigner was a pioneer in this field.
Yeah.
I mean, he was the one who introduced the concept of random matrices.
Yeah, to model those complex energy levels of heavy nuclei.
Exactly. That was groundbreaking work. And it laid the foundation for a whole new field of study.
It did, and it's amazing how his work continues to influence research today.
Absolutely. Now, out of Wigner's work came one of the most important examples, the Gaussian unitary ensemble, or GUE.
Yes. It's like the prototype for understanding random matrices.
It is. And it has this really cool connection to the Anderson model,
Oh, yeah, that's a fundamental model in condensed matter physics. It describes how electrons behave in a crystal lattice with impurities or defects.
Right, so you have this lattice, and the impurities cause disorder.
Exactly. And the amazing thing is that depending on how strong this disorder is, the electrons can be either delocalized or localized.
Oh, that's right. So delocalized means they're kind of spread out throughout the lattice.
Yeah, while localized means they're trapped in a small region.
That's such a cool concept. And this brings us to the heart of this paper. Random band matrices.
Yes, our main focus.
They have this special structure where the entries are non-zero only within a band along the diagonal.
Right, and the width of that band, the bandwidth, denoted by W, is super important.
It is, because it basically determines whether the system will exhibit localized or delocalized behavior.
So how does this bandwidth relate to the size of the matrix N?
That's a great question. And, there's this fascinating transition that's been observed and predicted by Thoules's conductance fluctuation theory, along with numerical simulations.
Okay, tell me more.
So when the bandwidth is much larger than the square root of the matrix size, WN 12, the system is expected to have delocalized eigenvectors and follow GUE statistics.
But when the bandwidth is much smaller...
Right, when WN 12...
things change.
They do. We see localized eigenvectors and Poisson statistics.
This transition is a key concept in random matrix theory. It helps us understand how disorder affects the behavior of these systems.
Absolutely. And you know what's really exciting about this paper?
What's that?
Well, they're actually trying to push the boundaries of what we know about this transition. They're using this new flow method to try to prove that delocalization holds for an even wider range of bandwidths.
That's ambitious. I'm eager to dive into the details.
Me too. So let's turn to page 2, where the authors really lay out their approach in detail.
Okay.
Their main goal is to show delocalization of bulk eigenvectors, specifically for a broad class of Gaussian random band matrices with general variance profiles.
And they emphasize that their result delocalization for bandwidth, WN811, is a big improvement over the previous best-known result of WN34.
Exactly. So they're making significant progress.
Absolutely. And to achieve this, they introduced this idea of quantum diffusion.
Oh, quantum diffusion. It's essential for understanding how this system behaves.
It is. They start by defining the discrete torus of length n, denoted as Tn.
Think of it like a circle with endpoints.
Right, and they explain how to measure distances on this torus.
It's all about setting up the mathematical framework.
Exactly. And then they introduce the doubly stochastic matrix S,
which captures the variance profile of the random band matrix.
Right. Its entries, denoted as sexy, represent the variance of the matrix element at position, x, y.
And don't forget the normalizing constant z and w day.
Oh, that's right. It ensures that the entries of S sum up to 1.
Now I have a question.
Shoot.
Why do they assume that S has a matrix square root S12?
Good question. Well, it actually simplifies things a bit.
Oh, how so?
The matrix square root allows them to express the random band matrix elements in a way that makes their analysis much easier.
Got it. So it's a technical convenience that helps them with the proof.
Exactly. Now, they formally define the Gaussian random band matrix ensemble as H and describe the properties of its entries,
Which are denoted as HXE.
Right, and these entries are Gaussian random variables with zero mean and variance determined by the corresponding entry of the matrix S.
So the matrix S is really controlling the structure of the randomness.
It is, and this definition sets the stage for analyzing the resolvent of this matrix.
Which is key for understanding both quantum diffusion and delocalization.
Exactly. Now, to study the resolvent, they introduce a powerful tool from random matrix theory. The Stieltjes transform of the Wigner semicircle law, denoted as MZ.
Okay, I remember the Stieltjes transform. It's a way to study the distribution of eigenvalues.
Right, and here they use it to analyze the Wigner semicircle law, which describes the global eigenvalue density.
And it's defined as mx dx, where there's the density of the Wigner semicircle law.
That's right. And there's this really interesting self-consistent equation that MZ satisfies. MZ is negative 1 plus MZ.
That equation links the Stieltjes transform to the spectral properties of the matrix.
Exactly. It's essential in many random matrix calculations.
Now, they also clarify the notation for the complex variable z equals e plus I.
Where E is a real number and E is positive.
This notation is crucial for defining the resolvent and for the flow method.
Right, and E in particular controls the smoothness of the resolvent.
It's a technical detail, but an important one.
Definitely. They also briefly explain the big O notation and stochastic domination as they'll be using them throughout the paper.
Oh yeah, those are common tools in random matrix theory.
They provide a way to express bounds on the size of things, but in a probabilistic sense.
So it's not just about saying something is less than a certain value, but about saying how likely it is to be less than that value.
Exactly. And these notations are essential when dealing with random matrices, especially as the matrix size grows large.
Okay, let's move on to page 3.
Sounds good.
Here, they define two key quantities: the T matrix, denoted as tab, and the diffusion profile.
Both of these are central to establishing the connection between quantum diffusion and the resolvent.
Right, so the T matrix, it basically tells us about the spreading of quantum particles in the system.
It's a way to measure the probability amplitude for a particle to transition from site A to site B.
And the diffusion profile.
Yeah.
It describes the expected behavior of a classical diffusion process on the discrete torus.
So we have the quantum T matrix and the classical, and the authors want to connect them.
Exactly. And they do this with theorem 2.
Ah, yes. This theorem states that the difference between TXC and XC is small under certain conditions.
Specifically, when W and 8 meet certain criteria.
Right. It says TXC XCA W2 and 212.
Where C is some constant.
This theorem is crucial. It establishes a quantitative link between the quantum dynamics and the classical diffusion process.
It's like saying that under the right conditions, the quantum system behaves almost like a classical random walk.
Which is an incredibly powerful way to visualize and understand the quantum dynamics.
The authors then connect the spectral gap of this random walk to the assumption, the W2N2.
The spectral gap is all about how fast the system reaches equilibrium, right?
Right. And this assumption ensures that we're looking at the system on a timescale where diffusive behavior is dominant.
So theorem 2 is essentially showing that diffusion holds up to the Thouless time, which is like the relaxation time of the random walk.
It's the time it takes for the system to kind of forget its initial state and settle into this diffusive behavior.
And all of this supports the idea that there's this transition at WN12, right?
It does. But, the authors also point out that proving quantum diffusion for the full range of bandwidths up to that point.
Up to WN12.
Yeah, it's still a big challenge.
Sounds like an exciting avenue for future research.
Absolutely.
Yeah.
Now, turning to page 4, we encounter the local law, theorem 4.
Okay, this theorem provides a bound on the difference between the entries of the resolvent matrix, GXI, and SEMSIC.
Right, and the bound is GXI, Gen C1.
This is another critical step towards proving eigenvector delocalization.
It is. It tells us that the resolvent entries are close to the Stieltjes transform, except for a small error term.
It's a local estimate, but it has big implications.
Definitely. The authors then introduce the concept of complete delocalization of bulk eigenvectors and the notation to describe it.
This is all about quantifying how spread out the eigenvectors are.
Exactly. And they use a projection operator, px, to help with this.
Right. This operator isolates the contribution of an eigenvector within a region of size around site x.
It's like shining a spotlight on a specific part of the eigenvector.
And then, with corollary 5, they use the local law to establish a bound on the density of eigenvectors that are localized to scale.
This corollary is telling us that most eigenvectors aren't localized to small regions.
It supports the delocalization result, providing further evidence for their main claim.
Exactly. And now we arrive at pages 5 through 14, where the real heavy lifting begins. It's the heart of the proof, where they bring out the big guns, mathematically speaking.
I'm ready for the challenge, are you?
Oh, absolutely. But I think this is a good place to take a breather and come back fresh for part 2 of our deep dives.
Sounds good to me. I can't wait to see how they tackle the technical details.
Me too. Until next time.
Okay, so we're picking up right where we left off, diving into the core of the proof on pages 5 through 14. And this is where the authors really flex their mathematical muscles. They start by applying Ito's lemma to derive SDEs for the Green's function, GTZ.
Oh, Ito's lemma. It's a powerful tool from stochastic calculus.
It is. It helps us understand how a function of a stochastic process changes over time.
And in this case, they use it to describe how the resolvent, represented by the Green's function, evolves over time.
Right, as the entries of the random band matrix fluctuate randomly.
Like a sort of Brownian motion.
Exactly. It's like watching the resolvent dance around as the matrix elements jiggle.
Now, to handle some tricky nonlinear terms that pop up in these SDEs.
Yeah, those can be a real headache.
They are. The authors introduce a stopping time.
Denoted as stop.
Right. This is a common technique in stochastic analysis.
It's like hitting the pause button on the system's evolution at certain points.
So you prevent things from blowing up mathematically.
Exactly. It's all about maintaining control over the analysis.
So how do they use this stopping time to prove their main result, Theorem 8?
Well, they construct a stop version of the dynamics,
Okay.
specifically for the difference between the T-matrix and the diffusion profile.
Which they denote as 8.
Right. And by stopping the evolution of certain terms at stop, they gain more control and can track the behavior of the system more easily.
It's like breaking down a complex process into smaller, more manageable chunks.
Exactly. Now, after setting up the stop dynamics, they dive into a series of lemmas.
Each one providing a crucial piece of the puzzle.
Right. They use a whole arsenal of techniques.
Like the von Neumann trace inequality and Ward's identity.
Oh, yes. Those are powerful tools in random matrix theory.
And the goal of all these lemmas is to show that the stopped version of 8
stay small
throughout the evolution, which implies that the stopping time is rarely triggered.
Exactly. If they can show that, then it directly leads to the proof of Theorem 8.
It's like building a strong case piece by piece.
It is. And each lemma is a carefully crafted argument that supports their main claim.
So can you give us a taste of what some of these lemmas are doing?
Sure. So lemma 9, for example.
Yeah.
It establishes a deterministic bound on a term that captures those nonlinear interactions we talked about earlier.
Okay.
The proof of this lemma relies heavily on the properties of the diffusion profile and careful analysis of the matrix square root, S12.
Right. It's all about using the tools they've developed to tame those tricky terms.
Exactly. Now, lemma 10 tackles a stochastic integral term.
Ah, those can be tricky.
They are. But the authors cleverly utilize martingale arguments and the Burkholder-Davis-Gundy inequality.
Okay, those sound pretty advanced.
They are, but they're essential for obtaining a stochastic domination estimate for this term.
So they're showing that this term stays small with high probability.
Precisely. It's all about controlling those random fluctuations.
And what about proposition 11? I've heard that one is particularly challenging.
You heard right. It's the heart of the proof, dealing with the drift term in the stopped dynamics.
Which they denote as ED stop.
Right. This term often represents the deterministic component of the evolution, and controlling it is crucial for the stability of the entire proof.
So it's like the foundation upon which everything else rests.
Exactly. And to handle this beast, they perform a series of integration by parts expansions.
To carefully control the interactions between the resolvent entries and the random matrix elements.
It's a delicate dance of mathematical concepts,
with each step bringing them closer to the final result.
It's really quite impressive.
Now, as we journey through these pages, we also encounter this clever change of variables technique in lemma 9.
Oh, yes. That helps them simplify the analysis and get sharper bounds.
It's always nice when a change of variables makes things easier.
It is. It's like finding the right lens to view a problem.
And to help us visualize the complex expansions, they introduce a diagrammatic notation.
Ah, yes. Visual aids are always appreciated, especially when dealing with such intricate
They
arguments.
are. So where does this diagrammatic notation come into play?
Well, on page 17, they use it to represent the terms that arise from those expansions.
To illustrate the process, right?
Exactly. Particularly in lemmas 18 and 19, where they apply the regular vertex expansion from lemma 16.
To break down certain graphs into simpler components.
It's a systematic way to categorize and analyze the different ways the resolvent can evolve.
Like sorting through a complex puzzle and finding the pieces that fit together.
And then there are those pesky fluctuation terms that we always have to worry about in stochastic analysis.
How do they keep those under control?
Well, they use a combination of techniques, like in lemma 22, where they analyze the moments of these terms.
To get balance on their behavior.
Right, and they also leverage the starting time construction to prevent these fluctuations from growing too large.
So it's like a safety net, catching any wild swings before they cause trouble.
Precisely. Controlling those fluctuations is essential for the robustness of the entire proof.
Okay, so as we approach page 15, are we getting close to the finish line?
We're getting there. Pages 15 and 16 focus on that crucial drift term, ED stop Z.
The deterministic part of the dynamics.
Right. They bring together all the previous lemmas and estimates to show that this term stays small.
Which, as we discussed, is essential for the stability of the proof.
Absolutely. They carefully explain their reasoning, highlighting the importance of those integration by parts expansions and the properties of the graphs involved.
It's like the grand finale where all the pieces come together.
It is. And by the end of page 16, they've successfully connected everything back to their main theorems, Theorem 2 and Theorem 4.
They show how each piece of the puzzle contributes to the overall picture.
It's a masterful display of mathematical precision and ingenuity.
Now, what awaits us on page 17?
Page 17 is kind of interesting. They step back a bit, and look at the bigger picture.
Oh, okay, so they're not just diving into more calculations.
Not really. They talk about refining their analysis, maybe loosening the restrictions on the bandwidth.
So pushing that delocalization result even further?
Exactly. Closer to that conjectured threshold of WN12.
They're really trying to push the boundaries here.
They are, and they even present this conjectured estimate equation 5.2.
And proving this could strengthen their results?
It could. It's all connected to the support length of G.
Okay. Remind me what that is again.
It basically measures how far the influence of a single entry in the resolvent extends spatially.
So it's about understanding how local changes affect the global behavior.
Exactly. And their idea is if we can get tighter bounds on the support length, then we might be able to relax the condition on the bandwidth and still see delocalization.
So it's like if we can show that local perturbations don't have a far-reaching effect.
Right. Then we might not need such a strong global constraint.
It's fascinating how everything is connected, the local and the global.
It is. This paper really highlights those intricate relationships.
It's a beautiful blend of rigorous math and deep physical insights.
Absolutely. A prime example of the power of mathematical physics.
Well, this has been a truly incredible deep dive. So much to unpack and think about.
It has. We've gone from the historical roots of random matrix theory all the way to the cutting edge of research.
We explored this fascinating transition between localized and delocalized behavior in random band matrices.
Learned about quantum diffusion, the role of the bandwidth,
and the author's ingenious use of a flow method to prove their results.
And those results, they're significant. They push our understanding of delocalization further than before.
And they open up new avenues for future research.
Exactly. There's still so much to explore in this field.
From our listeners, we encourage you to delve deeper into this paper.
Explore the concepts we've discussed.
And think about the broader implications of these findings.
For other areas of mathematical physics.
Until next time, keep those minds curious and those questions coming. All right, folks, get ready for a serious deep dive today. We're going to be tackling this paper, Quantum Diffusion and Delocalization in one-dimensional band matrices via the flow method.
Oh, this is a good one.
It is, right.
Yeah.
Dubova and Yang, these guys, they really went deep.
Yeah.
Published just this week, December 20, 2024. So hot off the presses.
Very cool. So
it's a dense one.
It is. It is. And you know what? I'm curious about the techniques, this flow method they're using. That seems to be like the...
Yeah, that's kind of the star of the show.
Star of the show, right.
Yeah.
So, but I guess maybe to set the stage, why is random matrix theory even important in physics? Like, what's the...
Okay.
Page 1 starts with Wigner.
Yeah. So Wigner had this really, really groundbreaking insight, and it's, I think it's easy to kind of to look back and think, oh, this is obvious. But he realized that the statistical properties of energy levels in complex quantum systems could be modeled using random matrices.
So it's like saying that, the energy levels of a heavy nucleus behave statistically similar to the eigenvalues of a random matrix. So there's this
universality.
Universality, right, yeah.
Yeah.
And this suggests that there's some deep underlying structure connecting all these seemingly disparate physical systems.
Yes. Yeah.
And so a prime example of this is what we call the Gaussian unitary ensemble, or GUE.
Right.
And this is a mean field model.
Okay.
So it's kind of like an average representation.
Okay.
And it captures the essence of this eigenvalue behavior in many complex systems.
So it was like our benchmark?
Yeah, it's a benchmark. It's a great starting point.
Okay.
But then they go on to talk about models that aren't mean field.
Right, and specifically the Anderson model, right?
Oh, yeah. So the Anderson model is super important here.
Oh.
It describes a particle moving on a lattice, but there's a twist.
Ooh, I love a twist.
The potential energy at each lattice site is random. So this randomness models disorder in the system.
Got it.
And the Anderson model has this Hamiltonian. It's written as delta plus lambda v.
Okay, so delta represents the particle hopping, right? Between sites, v is this random potential, and lambda is?
Lambda is the strength of the disorder.
Okay.
So think about it this way.
Yeah.
If lambda is large, those potential energy differences between sites are huge.
Okay.
It's like a really rugged landscape with deep valleys.
So the particle gets trapped.
Yeah, the particle gets trapped. And this corresponds to localized eigenvectors in the model.
High lambda stuck particle.
Exactly. Now, what about low lambda?
Low lambda?
Low lambda smooths out that energy landscape.
Okay.
It's like you're rolling a marble on a gentle slope.
So the particle's free to roam?
Yeah, the particle can move freely, and this corresponds to delocalized eigenvectors.
Okay.
And in this regime, the Anderson model starts to resemble the GUE more.
Interesting. So we've got this, spectrum of behavior, from, stuck to free, controlled by this lambda.
Exactly.
Okay.
And that's where random and matrices come in.
Okay.
So they provide another model that's also non-mean field.
Okay.
That exhibits this transition between localized and delocalized eigenvectors.
So they bridge the gap.
They bridge the gap between the GUE and the Anderson model.
Ah, I see. Okay. I'm starting to see the connections here.
Yeah.
So now the paper gets specific about the band matrix model they're using.
Right.
They mention Gaussian random variables and something called a variance profile. Sexy.
Right. So they're setting the stage for their analysis.
Okay.
The entries of their band matrix are Gaussian random variables with mean 0.
Okay.
So think of it as a matrix where most of the entries are 0, except for a band along the diagonal.
Okay, I can picture that.
And those non-zero entries are drawn from this Gaussian distribution.
Gotcha. All right. And what about this variance profile, Sexy? What does that tell us?
Yeah, so the variance profile basically describes how the variance of each entry depends on its position within the band.
Yeah.
And they define it using this symmetric probability density function f and a parameter w, which is the bandwidth.
So w controls how wide that band is.
Exactly.
Got it.
Yeah.
So page 2 dives into how these matrices are expected to behave.
Right. So page 2 introduces this crucial relationship between the bandwidth, W, and the matrix size, n.
Right.
So as n, the size of the matrix grows, the behavior depends on how W scales with n.
So the size of the playground matters.
Yeah, exactly. The size of the playground definitely matters.
Okay, so what are the different scenarios?
So there are two key regimes.
Yeah.
First, if W is much larger than the square root of n, denoted as W much greater than n to the 1/2,
Okay.
we expect delocalized eigenvectors.
Okay.
And in this regime, the local eigenvalue statistics resemble those of the GUE, our mean field model.
So wideband free-roaming particles, GUE-like behavior. Okay, that makes sense.
Yeah.
What's the other regime?
The opposite. So when W is much smaller than the square root of n, written as W much less than n to the 1/2,
Okay.
we anticipate a localized eigenvectors.
Yeah, right.
And in this regime, the eigenvalues behave more like a Poisson point process, indicating less correlation between them.
Narrowband, trapped particles, different statistics.
Exactly.
It mirrors the Anderson model.
Exactly, yeah.
Okay.
So the bandwidth W in the band matrix model acts like the inverse of the disorder strength 1 over lambda in the Anderson model.
Okay.
So increasing W is like decreasing lambda. Both lead to smoother energy landscapes and more delocalization.
Okay, that analogy helps.
Yeah.
So the paper that mentions focusing on the bulk of the spectrum, what does that mean exactly?
Right, so the spectrum refers to all the eigenvalues of a matrix.
Okay.
The bulk are those eigenvalues in the interior, away from the edges.
Okay.
And this distinction is important because eigenvalue and eigenvector behavior can differ significantly at the edges.
All right, the fringes.
Yeah, exactly. So we're zeroing in on the heart of the matrix here.
Right. Okay, so now this paper builds on previous work. Where did things stand before this research?
Right, so previous results has shown delocalization and GUE statistics for bandwidths satisfying W much greater than n to the 3/4.
Yeah.
On the other hand, localization was established for W much less than n to the 1/4.
So there's a gap.
So there's a gap between these thresholds, and this paper aims to narrow it.
Okay, so the goal is to push that delocalization threshold further down.
Exactly.
Okay, and they're using this idea of quantum diffusion to do it. How are those connected?
Right, so quantum diffusion is a way to describe the movement of quantum particles in a system.
Okay.
As if it were a classical diffusion process, like heat spreading.
Hmm?
And if you can prove quantum diffusion, it strongly suggests delocalized eigenvectors.
So proving diffusion means those particles aren't trapped, hence delocalization.
Exactly.
Got it. Okay, so page 3 introduces some serious math.
Yeah, it's getting real.
The Stieltjes transform and the Wigner semicircle law.
Yeah, so these are fundamental tools in random matrix theory.
Okay.
The Stieltjes transform, denoted M in the paper, is a function that helps us analyze the distribution of eigenvalues.
Okay.
And it's defined as, let me just.
I'm grabbing a pen.
Okay. Yeah.
Okay, you're saying.
Yeah. So the Stieltjes transform MZ is defined as MZ equals the integral of 1 over x minuses act row of x, where error of x is the probability measure associated with the eigenvalue distribution.
Okay.
And the really fascinating thing is that it satisfies a self-consistent equation.
Okay.
Which is key for a lot of calculations in random matrix theory.
All right, that's the Stieltjes transform. Now, what about this Wigner semicircle law?
Okay, so the Wigner semicircle law.
It sounds intriguing.
It describes the limiting distribution of eigenvalues for a large class of random matrices, including the GUE.
Okay.
So imagine you plot the eigenvalues of a large random matrix on a histogram. As the matrix size grows, that histogram's shape approaches a semicircle.
Oh, okay.
That's the Wigner semicircle law in action.
So it predicts the overall pattern of eigenvalues.
Exactly.
Okay.
And the Stieltjes transform of this semicircle distribution is the function MZ we just discussed.
Right.
The paper specifically mentions that Z, the argument of the Stieltjes transform, is a complex number defined as E plus E eta, with E being the real part and eta the imaginary part.
All right. Complex numbers coming into play.
Yeah.
I'm following.
This is crucial for understanding how the Stieltjes transform connects to the eigenvalue distribution.
Okay. What happens on page 4?
Okay, so page 4 introduces two key players, the T matrix, T abe, and the diffusion profile, Thabe.
All right, so the T matrix, give me like the
Yeah, so the T matrix is defined using the matrix square root of the variance profile and the resolvent.
Okay.
It gives us information about the local structure of the eigenvectors.
T matrix local eigenvector structure. Got it.
Yeah.
What about this diffusion profile?
So the diffusion profile, theta, is defined in terms of the Stieltjes transform and the variance profile.
Okay.
And it describes the expected behavior of the resolvent under quantum diffusion.
Okay, so theta is like our theoretical prediction for what we should see if diffusion is occurring.
Precisely.
Got it.
Now, the key result on this page is theorem 2.
Okay.
It states that under certain conditions on the bandwidth, the W and the imaginary part of the spectral parameter eta, the T matrix and the diffusion profile are approximately equal, denoted as T, approximately equal to theta.
So if key is approximately equal to theta, that's strong evidence for quantum diffusion.
Exactly.
Okay.
If our observed T matrix matches the theoretical diffusion profile, it supports the idea that the system exhibits quantum diffusion.
So the conditions required for this approximation to hold, are they spelled out?
Yeah, they dive into the specifics.
Okay.
We need eta to be proportional to W squared over N squared.
Okay. And WE to be greater than N to the 8/11ths by some small factor.
I'm noting those conditions, okay?
Yeah, these are essential for the math to work out.
All right, so we're looking for T approximately equal to theta as a sign of diffusion.
Right.
And this is where the flow method really shines, right?
Exactly. So the flow method allows us to track how the resolvent, and hence the T matrix,
Okay.
evolves as we change the imaginary part of the spectral parameter, eta,
Okay.
from an order 1 value down to the small scale where we're interested in studying the system.
So we're essentially zooming in on the behavior of the resolvent at smaller and smaller scales.
That's a good way to put it.
Okay.
Yeah, by analyzing how the resolvent evolves as we change eta, we can infer properties about the system, like whether or not quantum diffusion is taking place.
This is fascinating. Now, the paper mentions that the diffusion profile, theta, relates to a random walk on a torus. Can you unpack that for me?
Sure. So it turns out that theta is closely related to the resolvent of a classical diffusion operator,
Okay.
which in turn describes a random walk on a torus.
Okay.
And the step size of this random walk is connected to the bandwidth W.
So the behavior of our quantum particles can be likened to a classical random walk.
Exactly.
Right.
The fact that T is approximately equal to theta strengthens this analogy, suggesting that the quantum particles are moving around in a manner similar to this random walk on a torus.
That's a very intuitive way to understand what's going on.
Yeah.
Now, the authors briefly mention some technical challenges that prevent them from pushing their result all the way down to the conjectured threshold of W, much greater than N to the 1/2. What are those hurdles?
Right. They hint at some technical difficulties without delving into the specifics.
Okay.
But they suggest that with further refinements of the flow method, it might be possible to overcome these challenges
Right.
and push the result closer to the conjectured threshold.
Okay.
It's an area ripe for further research.
Always room for improvement.
Okay.
Okay. On to page 5.
We encounter the local law, a consequence of the quantum diffusion result.
Yeah.
What's that all about?
Okay, so the local law, stated as Theorem 4, gives us a powerful tool for analyzing the resolvents.
Okay.
Essentially, it bounds the difference between the resolvent entries and the Stieltjes transform,
Okay.
scaled appropriately by W to the -1, eta to the -1/2.
Okay.
This bound tells us that the resolvent closely approximates the Stieltjes transform, especially in the bulk of the spectrum where eta is not too small.
So the local law gives us a precise way to connect the resolvent to the Stieltjes transform, which, if you recall, encodes information about the eigenvalue distribution.
Exactly. And this local law directly follows from the quantum diffusion result established in Theorem 2.
Okay.
It's a beautiful example of how proving one key result can unlock a cascade of insights into the system.
And this local law is crucial for proving eigenvector delocalization, right?
Precisely. The local law provides the necessary control over the resolvent to deduce that the eigenvectors in the bulk of the spectrum are indeed delocalized.
Okay, so the logic flows. Quantum diffusion implies the local law, which then implies delocalization.
Exactly.
Got it. But the paper introduces some new notation on this page. Bic X, U alpha, and A epsilon L kappa.
Okay.
Can you walk me through those?
Sure. So pic X is a projection operator
Okay.
that focuses on the portion of a vector lying outside a ball of radius L around the index X. Think of it as a way to isolate part of a vector.
Okay.
U alpha represents an eigenvector corresponding to the eigenvalue lambda alpha.
So pic X applied to U alpha gives us the portion of that eigenvector outside a certain region around X.
Exactly.
Okay.
This helps quantify how spread out the eigenvector is.
Got it.
If a significant portion of the eigenvector lies outside this region, it suggests delocalization.
Okay, and what about that set A epsilon L kappa?
Okay, so A epsilon L kappa is a set containing all eigenvectors associated with bulk eigenvalues that are localized to a length scale, IL, up to a small error epsilon.
Oh.
Think of it as the collection of eigenvectors that are mostly concentrated within a region of size IL.
So if A epsilon L kappa is small, That means there aren't many localized eigenvectors.
Exactly.
Right.
That's the point of Corollary 5,
Okay.
which uses the local law and previous work by Erdos and Knowles to demonstrate that the density of localized eigenvectors in the bulk is indeed small.
Uh-huh. So the local law tells us most eigenvectors are not concentrated in small regions, which implies delocalization.
Precisely.
It's a beautiful chain of reasoning, and it all hinges on the quantum diffusion result.
Yeah, it all comes together.
Amazing how it all comes together. Page 6 briefly summarizes the rest of the paper.
Right.
What can we expect in the remaining sections?
So the rest of the paper is dedicated to proving the results we've discussed so far,
Okay.
particularly Theorem 2, which established the quantum diffusion.
Right.
It's going to get quite technical, involving a deep dive into the flow method and its application to this specific random band matrix model.
Bring on the technicalities. I'm ready to see how they built this mathematical machinery.
Okay, great.
What's first on the agenda?
So first, we'll delve into pages 7 through 14, where the authors lay the groundwork for the flow method by introducing a process denoted HT.
Okay.
This process evolves over time,
Okay.
and its entries are defined using Brownian motions.
Brownian motion. So we're introducing randomness into the system.
Exactly. Brownian motions are a mathematical way to model random fluctuations.
Oh,
And here they're used to model the evolution of the matrix entries over time.
interesting. So our matrix is no longer static.
Yeah,
It's changing randomly over time.
precisely.
I like it.
This time-dependent nature is at the heart of the flow method.
Okay.
The authors then define a path,
Okay.
which depends on the Stieltjes transform, mz, and the time parameter 2.
Okay.
And this path dictates how a parameter related to the resolvent will change over time.
So we're guiding the evolution of the resolvent along a specific path.
Exactly. This controlled evolution is key to the analysis.
Okay.
They then introduce the time-dependent resolvent, GT,
Okay.
which is the resolvent of the evolving matrix HT,
Okay.
evaluated at the point when.
So as our matrix HT evolves randomly,
Yeah.
we're tracking how its resolvent changes along this predetermined path DUT.
Precisely.
I'm following so far.
Excellent.
This is great.
Then they introduce the time-dependent T matrix,
Okay.
which is defined analogously to the static T matrix,
Okay.
but now using the time-dependent resolvent.
Okay, so we have time-dependent versions of both the resolvent and the T matrix.
Right.
I'm sensing a pattern here. Introduce time dependence, define the time-dependent quantities,
Right.
and then...
And then we derive equations that govern their evolution.
Right.
The authors use Ito's lemma,
Oh, Ito's lemma,
powerful tool from stochastic calculus,
the classic.
to derive stochastic differential equations, or SDEs,
Okay.
that describe how GT change over time.
So we're essentially capturing the dynamics of these matrices as they evolve randomly.
Precisely.
Okay.
These SDEs are the heart of the flow method.
Got it.
They allow us to study the behavior of the resolvent and the T matrix as they're subjected to these random fluctuations.
Okay. I'm starting to appreciate the power of this approach. It's like watching a movie of these matrices evolving instead of just looking at a static snapshot.
That's a great way to put it.
Yeah.
And remember the diffusion profile, theta?
Yeah,
Well, they introduce a time-dependent version of it,
of course.
denoted theta t,
Makes sense.
which also evolves according to a differential equation.
So we now have these two quantities, T to T evolving side by side. I bet the goal is to show they stay close to each other.
You're absolutely right.
Right.
To quantify this, they define EAT as the difference between TT and theta t.
Okay.
It represents the deviation of the T matrix from the expected behavior under quantum diffusion.
So EAT is like our error term, measuring how far we are from the ideal diffusion scenario.
Exactly.
Okay.
The authors derive an SDE for EAT
Okay.
and express it in integral form, breaking it down into 3 components.
Okay.
HE NDT representing the martingale part, EDT representing the drift term,
Okay.
and EAS containing the nonlinear terms.
Okay.
Analyzing each component individually will be crucial for understanding the overall behavior of EATs.
Divide and conquer. It sounds like a solid strategy.
It is.
Yeah.
Now, analyzing these components,
Yeah.
particularly that drift term EDT, is where things get really technical.
Okay. I was waiting for the other shoe to drop.
Yeah.
Okay. So what are we talking about here?
This is where they'll employ a technique called renormalization,
Okay.
which is essentially a way to carefully manipulate the terms in the integral equation
Okay.
to extract the dominant contributions and handle potentially problematic terms.
So it's a way to tame mathematical infinities.
Yeah, you could think of it that way.
Sounds powerful.
It is powerful. It's a very powerful technique. In this specific case, the authors use renormalization to handle integration by parts expansions,
Okay.
which they use to analyze the drift term.
Got it.
They introduced definition 15 on page 19, which formally defines their renormalization procedure.
Okay.
It involves subtracting a specific term from the original expression,
Okay.
and this subtraction is designed to cancel out potential divergences.
So it's a carefully crafted subtraction to remove those problematic infinities.
Exactly.
Okay, what does this subtracted term look like?
So the subtracted term involves the derivative of the function
Okay.
with respect to the matrix entries.
Okay.
It's a bit technical, but the key is that it's chosen in such a way that it precisely counteracts the potential divergences arising from the integration by parts procedure.
I see. So by subtracting this carefully chosen term, they're ensuring that the resulting expression is well-behaved and finite.
Exactly.
Okay, what happens next?
Next, they introduce lemma 16,
Go ahead.
which contains the loop and regular vertex expansions. These expansions are key tools for manipulating the resolvent
Okay.
and expressing it in terms of simpler quantities.
Okay.
The loop expansion focuses on analyzing individual diagonal entries of the resolvent,
Go.
while the regular vertex expansion deals with pairs of resolvent entries.
So they're breaking down the resolvent, which can be a complicated object, into more manageable pieces using these expansions.
Exactly. It's like taking a complex machine apart to understand how its individual components work.
Right.
And to make things even more intuitive, they introduce a diagrammatic notation presented in definition 17.
Yes, the visual aids. I love it when they do that.
Yeah, these are great.
I'm curious to see how those come into play here.
This definition formalizes how to represent each term in the loop and regular vertex expansions visually.
Okay.
Each element in the diagram, like a line, a vertex, or wavy line,
Okay.
represents a specific mathematical factor in the expression.
So each diagram is like a blueprint for a mathematical term.
That's a great analogy. The authors provide a clear guide for interpreting these diagrams, so you can easily translate back and forth between the visual representation and the corresponding mathematical expression.
Okay.
For instance, a solid line represents a resolvent entry.
Okay.
A delta symbol indicates the difference between a resolvent entry and the Stieltjes transform.
Okay.
And a wavy line represents a variance profile entry or its inverse.
So it's a way to streamline the analysis and make it more visually appealing.
Yeah, exactly.
I'm ready for some diagram action. Where do they appear?
All right, so lemmas 18 and 19 demonstrate how to use the loop and regular vertex expansions to decompose the initial diagram,
Okay.
representing the integrand in ED, stop Z, into a series of simpler diagrams.
So they start with a complex diagram representing the drift term, and then they use these expansions to break it down into smaller, easier to analyze diagrams.
Exactly. It's like taking apart a complicated Lego structure and studying the individual bricks.
Okay.
Each new diagram represents a term that needs to be carefully analyzed and bounded.
Got it.
Lemmas 20, 21, and 22 provide the necessary bounds on these individual diagrams.
Okay.
And the diagrammatic notation makes the analysis much more intuitive.
So it's like a systematic approach to bounding the drift term one diagram at a time.
Precisely.
Okay.
The authors carefully track the evolution of the diagrams as they apply the expansions,
Okay.
noting how the number of lines, vertices, and wavy lines changes with each step.
Right.
They use this information to derive bounds on the diagrams, ultimately leading to the desired bound on the drift term.
This is where the art of mathematical bookkeeping really shines. They're keeping track of all these moving parts, these diagrams transforming, and it all leads to a precise bound on the drift term.
Exactly. It's a testament to the power of combining rigorous analysis with clever notation.
I love it.
By carefully manipulating these diagrams and applying the appropriate bounds,
Yeah.
they're able to establish proposition 11, which, if you recall, provides the crucial bound on the drift term, ED, stop Z.
And that was the missing piece of the puzzle.
Yes.
With proposition 11 proven, the entire proof of theorem 2, the quantum diffusion result, is complete.
Exactly.
It's like they've built a mathematical bridge connecting all these concepts together.
That's a great way to put it. It's remarkable how they weave together stochastic, calculus, analysis, and combinatorics to arrive at this profound result.
Now, on page 28, they hint at some potential refinements and further avenues of research, right?
Yeah.
They mentioned some conjectures that could lead to even stronger results. What are those about?
Right. So they present two conjectures, 5.1 and 5.2,
Okay.
involving operator norms of certain combinations of the resolvent AES,
Okay.
and the variance profile matrices, SU.
Operator norms, those measure the size of an operator, right?
Exactly.
How much it can stretch or shrink a vector.
Yeah, that's a good way to think about it.
Okay.
The authors believe that if these conjectures regarding these specific operator norms are proven,
Okay.
they could lead to a sharper result for delocalization, potentially pushing the threshold for W is even closer to the conjectured value of W, much greater than n to the 1/2.
So even after all this groundbreaking work, there's still more to explore.
Yeah, always.
What's the intuition behind these conjectures? Why do they believe these operator norms might be bounded in this way?
The authors suggest that their current analysis might not be fully exploiting the specific structure of the variance profile matrix and its square root.
Okay.
They believe that a deeper understanding of how these matrices interact with the resolvent could lead to tighter bounds on the relevant quantities.
So it's like they've laid the foundation, but there's still room to optimize the design of the building, so to speak.
That's a great analogy.
Okay.
They've built a powerful framework, and these conjectures point towards potential ways to refine and strengthen that framework.
Right, right.
It's exciting to think about what future research might uncover.
I completely agree. Now, before we wrap up this incredible deep dive,
Yeah.
I have to admit my brain is a bit overloaded with all these details.
Yeah.
Could we take a step back and revisit the big picture? What were the key milestones on this mathematical journey?
Certainly, let's recap the highlights.
Sounds good. Let me grab a sip of water and get ready to summarize. Okay. I'm ready to unpack this renormalization procedure. Sounds like a heavy-duty mathematical tool.
It is, but it's a crucial one for handling certain types of calculations in random matrix theory. In this paper, it's used to tackle that tricky drift term, ED, stopped Z, which we encountered in the integral form of the stopped process.
Right, ED stop. That's where things started to get really hairy. So how does renormalization help?
Renormalization essentially helps us deal with potentially divergent or infinite terms that can arise in calculations. It's like a way to extract meaningful, finite results from expressions that might otherwise seem nonsensical.
So it's a way to tame mathematical infinities. Sounds powerful.
It is. In this specific case, the authors use renormalization to handle integration by parts expansions, which they use to analyze the drift term. They introduced definition 15 on page 19, which formally defines their renormalization procedure. It involves subtracting a specific term from the original expression, and this subtraction is designed to cancel out potential divergences.
Okay, so it's a carefully crafted subtraction to remove those problematic infinities. What does this subtracted term look like?
The subtracted term involves the derivative of the function with respect to the matrix entries. It's a bit technical, but the key is that it's chosen in such a way that it precisely counteracts the potential divergences arising from the integration by parts procedure.
I see. So by subtracting this carefully chosen term, they're ensuring that the resulting expression is well-behaved and finite. What happens next?
Next, they introduce lemma 16, which contains the loop and regular vertex expansions. These expansions are key tools for manipulating the resolvent and expressing it in terms of simpler quantities. The loop expansion focuses on analyzing individual diagonal entries of the resolvent, while the regular vertex expansion deals with pairs of resolvent entries.
Okay, so they're breaking down the resolvent, which can be a complicated object, into more manageable pieces using these expansions.
Exactly. It's like taking a complex machine apart to understand how its individual components work. And to make things even more intuitive, they introduce a diagrammatic notation presented in definition 17. Remember, we talked about diagrams before?
Yes. The visual aids. I'm curious to see how those come into play here.
This definition formalizes how to represent each term in the loop and regular vertex expansions visually. Each element in the diagram, like a line, a vertex, or a wavy line, represents a specific mathematical factor in the expression.
So each diagram is like a blueprint for a mathematical term.
That's a great analogy. The authors provide a clear guide for interpreting these diagrams, so you can easily translate back and forth between the visual representation and the corresponding mathematical expression. For instance, a solid line represents a resolvent entry, a delta symbol indicates the difference between a resolvent entry and the Stieltjes transform, and a wavy line represents a variance profile entry or its inverse.
Okay, so it's a way to streamline the analysis and make it more visually appealing. I'm ready for some diagram action. Where do they appear?
Lemmas 18 and 19 demonstrate how to use the loop and regular vertex expansions to decompose the initial diagram representing the integrand in ED, stop SU, into a series of simpler diagrams.
So they start with a complex diagram representing the drift term, and then they use these expansions to break it down into smaller, easier to analyze diagrams.
Exactly. It's like taking apart a complicated Lego structure and studying the individual bricks. Each new diagram represents a term that needs to be carefully analyzed and bounded. Lemmas 20, 21, and 22 provide the necessary bounds on these individual diagrams, and the diagrammatic notation makes the analysis much more intuitive.
So it's like a systematic approach to bounding the drift term, one diagram at a time.
Precisely. The authors carefully track the evolution of the diagrams as they apply the expansions, noting how the number of lines, vertices, and wavy lines changes with each step. They use this information to derive bounds on the diagrams, ultimately leading to the desired bound on the drift term.
This is where the art of mathematical bookkeeping really shines. They're keeping track of all these moving parts, these diagrams transforming, and it all leads to a precise bound on the drift term.
Exactly. It's a testament to the power of combining rigorous analysis with clever notation. By carefully manipulating these diagrams and applying the appropriate bounds, they're able to establish Proposition 11, which, if you recall, provides the crucial bound on the drift term EE, stuck.
And that was the missing piece of the puzzle. With Proposition 11 proven, the entire proof of Theorem 2, the quantum diffusion result, is complete. It's like they've built a mathematical bridge connecting all these concepts together.
That's a great way to put it. It's remarkable how they weave together stochastic calculus, analysis, and combinatorics to arrive at this profound result.
Now on page 28, they hint at some potential refinements and further avenues of research, right? They mention some conjectures that could lead to even stronger results.
Yes, they present two conjectures, 5.1 and 5.2, involving operator norms of certain combinations of the resolvent GS and the variance profile matrices SU.
Operator norms, those measure the size of an operator, right? How much it can stretch or shrink a vector.
Exactly. The authors believe that if these conjectures regarding these specific operator norms are proven, they could lead to a sharper result for delocalization, potentially pushing the threshold for W even closer to the conjectured value of W, much greater than n to the 1/2.
So even after all this groundbreaking work, there's still more to explore.
Always. The pursuit of knowledge is a never-ending journey, and this paper has illuminated a path toward a deeper understanding of these fascinating random systems.
What a fantastic way to end our deep dive. To our listeners who've joined us on this mathematical adventure, I encourage you to keep exploring, keep questioning, and keep pushing the boundaries of knowledge. Until next time, happy diving. All right, brain rebooted, ready for that recap, expert speaker. Okay, so we started by understanding why random matrix theory is so powerful for analyzing complex quantum systems. We revisited Wigner's idea of universality, the concept of mean field models like the GUE, and the importance of models that incorporate disorder like the Anderson model, right? Those models provided the context for understanding the specific band matrix model that Dubova and Yang investigate.
Exactly. We saw how their model exhibits a transition between localized and delocalized eigenvectors, depending on the relationship between the bandwidth W and the matrix size n.
And their goal was to push the known threshold for delocalization further, right?
Yeah, precisely. They wanted to show that delocalization occurs for even smaller bandwidth than previously established.
And to do that, they introduced this fascinating concept of quantum diffusion.
Yes, quantum diffusion provides a way to connect the behavior of quantum particles to a classical diffusion process, like a random walk on a torus. They aim to prove that quantum diffusion occurs in their band matrix model, as that would strongly suggest delocalized eigenvectors.
Okay, so proving quantum diffusion was a key objective. What were the main tools they used to achieve that?
They employed a combination of sophisticated techniques, including the Stieltjes transform, the Wigner semicircle law, and most importantly, the flow method.
The flow method that was the real star of the show. Can you remind me how that worked?
Certainly. The flow method involved introducing a time-dependent process and studying how certain key quantities, like the resolvent and the T-matrix, evolve over time. They derived stochastic differential equations, or SDEs, to describe these dynamics, and they introduced a clever stopping time argument to control the analysis.
Right. Those stopping times were like safeguards to ensure their calculations didn't go off the rails.
Exactly. And a major part of their analysis involved proving that these stopping times wouldn't interfere with their results.
And they also relied heavily on Green's function estimates to understand the behavior of the resolvent. I remember those involved some tricky calculations using resolvent identities and Ward's identity.
Yes, those estimates were crucial for controlling the resolvent and ultimately proving the main results.
And then there was that whole renormalization procedure with those fascinating diagrams.
Ah, yes, the diagrams. Those were a stroke of genius, allowing them to visualize and manipulate the terms arising from the integration by parts expansions. It was like a form of mathematical art.
It really was. So after all that mathematical heavy lifting, What was the ultimate outcome? Did they achieve their goal?
They did. They successfully established quantum diffusion in their band matrix model for a wider range of bandwidths than previously known. This result, stated as Theorem 2, is a major contribution to the field.
So they pushed the boundaries of our understanding of delocalization. What are the implications of this result? Why should we care about delocalization in random band matrices?
This result has significant implications for our understanding of complex quantum systems. Random matrix theory provides a powerful framework for modeling such systems, and this work sheds new light on the behavior of eigenvectors, which play a crucial role in determining the physical properties of these systems.
So it's not just an abstract mathematical exercise, it has real-world connections.
Absolutely. For example, these findings could inform our understanding of electron transport in disordered materials, the behavior of complex networks, or even the dynamics of financial markets.
Wow, that's quite a range of applications.
Indeed, the beauty of mathematics lies in its ability to connect seemingly disparate areas and to reveal hidden patterns that govern the world around us.
Well said. This has been a truly mind-bending deep dive.
Yeah.
But I feel like I've gained a much deeper appreciation for the power and elegance of random matrix theory.
I'm glad to hear that. It's always rewarding to delve into these fascinating areas of research and to see how mathematical ingenuity can lead to such profound insights.
And the story doesn't end here, right?
Mm-hmm.
They hinted at some potential avenues for future research.
Yes, they presented a couple of conjectures that, if proven, could further sharpen the results and potentially push the delocalization threshold even closer to the conjectured value.
So there's still more to discover, more mysteries to unravel.
Always. The pursuit of knowledge is a never-ending journey, and this paper has illuminated a path toward a deeper understanding of these fascinating random systems.
Absolutely. And on that note, I think we're going to wrap up this deep dive. I want to thank our expert for walking us through this incredible paper.
It's been my pleasure.
And to all of you listening out there, we'll see you next time for another deep dive into the world of math and science. Welcome back, everyone, for another deep dive. I always say that, right? Another deep dive.
Always exciting.
It is always exciting to dive deep into a new paper. And today we have
A fresh one.
a fresh one. Hot off the press, quantum diffusion and delocalization in one-dimensional band matrices via the flow method from December 20th, 2024. So just came out.
Yeah, just came out.
Very recently. And I know that our listeners are ready to get into some serious math.
They're ready.
So we're going to go deep. We're going to go deep into the proof.
Sounds good.
All right. So without further ado, this paper is about what? What are we looking at here?
So this paper looks at random matrix theory, a very exciting area. It has a lot of implications for different fields.
Dynamic field theory.
And specifically, it looks at the behavior of eigenvectors in random band matrices.
Okay.
And the question is, are these eigenvectors delocalized or are they localized?
Okay. So delocalized means they're spread out.
Yeah, they're spread out.
And localized means they're concentrated.
Yeah, they're concentrated in specific regions.
In a particular region. Okay.
And what this paper tries to do is to prove delocalization for a broad class of these matrices under certain conditions.
Okay.
And they're pushing beyond what we already know. So previous work focused on delocalization when the bandwidth W is much larger than n to the power of 3/4.
Okay.
So this paper is trying to push it to when W is much larger than n to the power of 811.
Wow. Okay. So we're really pushing the boundary here.
Pushing the boundaries.
Of what we know.
Yeah.
Okay. And they do this using a new tool, a new method called the flow method, which I'm excited to learn more about.
Yeah, it's very intriguing. It introduces the concept of time, and they use Brownian motion to analyze what's called the resolvent.
Oh, okay. So that's where the flow comes in.
The flow, yeah.
Okay. So we'll be exploring that. We'll be exploring quantum diffusion.
Yes.
Connecting it to the idea of random walks, which a lot of people might be more familiar with, and understanding why that threshold of WN12 is so important for the whole eigenvector localization thing.
Yeah, why is that threshold so important? We'll get into that.
Yeah, we'll get into that.
Okay.
So I'm looking at page 1.
Okay.
And it looks like they're starting by comparing two different models, right? The Gaussian unitary ensemble, the GUE.
Yeah, that's one.
And then the Anderson model.
Yes.
Can you talk about why they're starting with this comparison?
Sure. So the GUE is very well studied, and we know that the eigenvectors in that model are delocalized. The Anderson model, on the other hand, is also well studied, but the eigenvectors there are localized. So what they want to highlight is that random band matrices kind of exhibit a similar transition between these two types of statistics.
Oh, interesting. So they're kind of in between these two models that have already been very well studied.
Exactly.
Okay, that makes sense. And this is fascinating to me because it kind of shows how these different systems, even though they seem very different on the surface, they share this underlying mathematical structure. Okay, all right. And then they define what these random band matrices are.
Yeah.
So can you give us a picture of what we're actually talking about here?
Sure. So imagine you have a square matrix. It has random entries, but these random entries are only within a certain band around the diagonal.
Yeah, a band around the diagonal.
Yeah, and this band has a certain width, and that's denoted by W.
Okay.
And it turns out that the size of this band relative to the size of the matrix N dictates whether we see delocalized or localized eigenvectors.
Okay, so the size of the band W relative to the size of the matrix N is really important here.
Yeah, it's crucial.
Okay.
And that leads us to this core conjecture that if W is much larger than the square root of N,
Okay.
we get delocalization.
Delocalize eigenvectors.
If it's much smaller,
If W is much smaller.
then we get localized eigenvectors.
Localized. Okay. So that's the core idea that we're working with.
Yeah, that's the conjecture that this whole field is trying to prove.
Okay. And then they move into a bit of the history of this problem.
Right.
Talking about previous research and its limitations.
Exactly.
Why is it important to include this historical context?
Well, it shows how this problem has been tackled in the past. What were the limitations of the previous approaches and why this current paper is actually a breakthrough.
Okay. So it's setting the stage for their contribution.
Right.
Got it. All right. Flipping the page to page 2.
Okay, page 2.
It looks like now we're getting into the nitty-gritty math.
Yes.
They're defining the specific model they're using.
Right.
So what kind of random band matrices are we working with here?
So they're using what are called Gaussian random band matrices.
Okay.
But with a twist. They have what's called a general variance profile, which is denoted by S.
Okay.
And this variance profile is determined by a symmetric probability density function, F.
Okay, so S is the variance profile. X is the probability density function.
Yeah.
And what does that variance profile actually do?
So the variance profile tells us how the randomness is distributed within the band.
Oh, okay. So it's not just uniform randomness. It can vary
It can vary.
within the band.
Okay.
And then we encounter this, it looks like a very important concept called the Stieltjes transform.
Oh, yeah. That's a cornerstone of random matrix theory.
Okay. And it's denoted by MZ. Can you tell us a little bit about what this transform does?
So the Stieltjes transform is basically a tool that allows us to study the spectral properties of the matrix.
Okay, so the spectrum meaning the eigenvalues.
The eigenvalues, right?
Yeah.
And it's linked to this spectral parameter Z, which is expressed as E plus E.
Okay, E plus I, where E is real and E is positive.
Correct.
Got it. So this Z kind of tells us where we are in the spectrum.
Yeah, it allows us to probe different regions
Right.
of the spectrum.
Okay, so the Stieltjes transform is all about understanding those spectral properties.
Yes.
All right. And then they introduce two more important matrices. The T matrix, denoted by T, and the diffusion profile. What do these matrices represent?
So the T matrix, that one captures information about eigenvector localization.
Okay.
And it's constructed from what's called the resolvent, which encodes the spectral properties of the matrix.
Okay.
Now, the diffusion profile, that one describes the expected behavior under something called quantum diffusion.
Okay.
And this describes the expected behavior of a diffusion process on a torus.
Okay. Interesting. So the T matrix is all about localization and the diffusion profile is about diffusion.
Right.
Okay. And then we get to their main result, Theorem 2.
Yes.
So what does Theorem 2 tell us?
It says that under specific conditions, and the conditions are W much larger than N to the power of 811 plus U,
Okay.
and E proportional to W squared N to the power of -2.
Okay, so those are the specific conditions.
Yeah, it says that the T matrix and the diffusion profile are very, very close.
Okay, so they become almost the same thing.
Almost the same thing, yeah. And what this implies is that quantum diffusion is at play.
Oh, interesting. Okay, so that closeness tells us that we have quantum diffusion.
Yes. It means that we can link the behavior of this random band matrix to that of a classical diffusion process, like a random walk on a torus.
Oh, okay, so it's connecting back to something more familiar, a random walk.
Yeah.
And how does all of this relate back to that threshold of WA and 12 that we talked about earlier?
Right. So it turns out that near this threshold, The relaxation time of the random walk and the spacing between the eigenvalues and the matrix model, they become comparable.
Okay, so that's why that threshold is so important. It's
Yeah.
where those two things kind of line up.
Exactly.
The random walk and the eigenvalues.
Yeah. And this page really lays the foundation for the rest of the proof.
Okay, so we've got our models, we've got our key matrices, we've got our main theorem.
Uh-huh.
We're ready to dive deeper.
Let's do it.
All right. Page 3. Looks like we're introducing a new approach here. The stochastic differential equation, the SDE approach.
Yeah, this is a novel tool in this context.
Yeah.
And what they do is they use this SDE to analyze the evolution of the T matrix
Okay.
over time.
So we're introducing a time parameter here.
Yes. So we can study how the T matrix changes dynamically.
Okay. So it's like watching a movie of the T matrix as it evolves.
Exactly.
I like that. And then they introduce this idea of a stopped version of the T matrix dynamics,
Yeah.
which is denoted by S-stop, and the concepts of stopping times. Stop. To control the growth of certain terms in the SDE.
Yeah, so stopping times are very powerful. In stochastic analysis, they allow you to analyze a process up to a certain point, chosen strategically,
Okay.
to simplify things.
I see.
So in this case, they want to prevent certain terms from becoming too large
Yeah.
and difficult to control.
So it's like hitting the pause button on the movie at just the right moment
Exact.
to get a clear snapshot of what's happening.
Oh, yeah.
And Theorem 8, what does that tell us?
So Theorem 8 establishes that this stopping time construction is effective. It paves the way for their main results.
Okay, so this is kind of setting us up for what's to come. All right, now we're on page 4. Looks like they're really getting into the details of this SDE and specifically this drift term.
Yeah, the drift term. And they use diagrams to help us visualize this.
Okay, so these aren't just pretty pictures. These diagrams are actually representing something important.
Yeah, they represent a powerful technique called graphical expansion,
Okay.
which allows us to simplify complex expressions.
So it's like breaking down a complicated dance move into a sequence of simpler steps.
Yeah, exactly.
Okay, that makes sense. So lemma 16 is where they're describing the rules of this graphical language.
Yeah, the rules. So how we connect these mathematical objects like matrices and resolvent entries to these elements in the diagram.
So it's like a dictionary.
A dictionary, yeah.
Translating between the math and the pictures.
Exactly.
And then definition 17 provides that visual representation of the drift term
Yeah.
in equation 4.2, which is then further broken down into simpler graphs using lemma 18.
Right. And this is key. We need to break it down into these smaller pieces
Okay, why is that so important?
because we can then analyze each piece separately and then combine the results.
So it's like a divide and conquer strategy.
Divide and conquer, yeah.
All right. So we've broken down this drift term into these smaller graphs. Moving on to page 5,
Okay.
we see the iterative expansion of these graphs from lemma 18 taking center stage.
Yes. And this is where things start to get really tricky.
Okay.
We have to keep track of all these terms as they become increasingly complex.
So it's like that dance sequence is getting more and more intricate,
Yeah.
and we need to make sure we don't miss a step.
Exactly.
And lemma 20 comes in to provide bounds on the main terms
Yeah.
arising from these expansions.
Yes.
And they link these bounds to the size of the imaginary part of the spectral parameter, which is denoted by IMWIT.
Right. And these bounds are crucial to make sure that things don't blow up,
Okay.
to make sure those terms don't grow too large.
So it's like keeping the dancers within the boundaries of the stage.
Yeah, good analogy.
And then lemma 21 tackles the integration by parts terms.
Right. Another type of term that comes up in the expansion.
Okay. And again, relating the bounds to IMPT.
Yes.
So we're seeing a pattern here.
A pattern.
IMPT seems to be playing a very important role.
It is. It's a key parameter in controlling the growth of these terms.
Okay. And these lemmas, with their very meticulous estimates,
Uh-huh.
really highlight the technical rigor of this paper.
Yeah, they're not cutting any corners.
No, they're not. Right. Page 6. We're at the final step, controlling the fluctuation terms from the graphical expansion.
Yes.
Lemma 22 provides the bounds. And they achieve this using moment calculations and the Chebyshev inequality.
Yes.
Can you tell us a little bit about what these tools do?
Sure. So moment calculations give you information about the distribution of a random variable.
Yeah.
And Chebyshev's inequality gives you bounds on the probability of deviations from the mean.
Okay.
So by combining these two, you can control the fluctuations.
So we're making sure that those fluctuations don't kind of take over,
Exactly.
dominate the behavior of the system.
Right.
And all of these lemmas together establish proposition 11.
Yes.
which effectively controls the crucial drift term.
Right. So Proposition 11 is a very important stepping stone in their proof.
Okay.
It makes sure that the drift term,
Which represents what again?
it represents the deterministic part of the T-matrix's evolution.
Okay.
It makes sure it stays within acceptable bounds.
Okay.
And that is essential for proving their main results.
Got it. Okay. So we've now reached section 3,
Okay.
where they lay out this really cool machinery of the flow method.
The flow method, yeah. So we're introducing a time parameter, t.
Okay.
And we're going to study the evolution of the resolvent g sub t of z
Okay.
along a specific path in the complex plane.
So imagine the resolvent as a point moving along this path.
Right.
And the flow method allows us to study how its properties change.
Exactly, as it travels.
And ultimately, this will lead us to conclusions about the eigenvector behavior.
That's the goal.
Okay. And they define this path very cleverly. Starting at t equals 0, with w sub t equals z plus m of z.
Right.
And ending at t equals 1, with w1 equals z.
Yeah.
Where z is our spectral parameter, and m of z is the Stieltjes transform.
Yes. So the choice of path is very important.
Okay. Why is that?
Because it ensures that the resolvent starts at a point determined by the global spectral properties of the matrix,
Okay.
which is encoded in the Stieltjes transform, and it flows towards a specific point in the spectrum,
Okay.
determined by z.
Got it.
And this controlled evolution allows for a precise analysis.
Okay. So we're starting from something global and moving to something specific.
Exactly.
And that's how we're going to get our precise results.
Yes.
Okay. Now, the magic happens when they express the entries of the random band matrix H as Brownian motions.
Brownian motions, yeah.
And this allows them to derive an SDE describing how the resolvent changes with time.
That's right. So we're connecting the random nature of the matrix to a well-studied stochastic process.
Brownian motion.
Brownian motion, exactly.
And that SDE captures the interplay between that randomness and the deterministic evolution of the flow method.
Exactly.
Can we actually see this SDE?
Sure. So they present it in lemma 6, and it looks like this. dg sub t of z equals negative g sub t of z, d sub t, g sub t of z plus g sub t of z times s of g sub t of z minus m of z times g sub t of z dt.
Okay. That is a mouthful.
It is, yeah.
Can you break it down for us a little bit?
Yeah, sure. So the first term, that captures the random fluctuation
Okay.
caused by the Brownian motion
Okay.
of the matrix entries. So it's the unpredictable jiggles.
Okay.
The jiggles. Yeah, as the resolvent moves along the path.
Okay. So that's the randomness. What about the second term?
So the second term represents the deterministic drift
Okay.
that guides the resolvent.
Okay. So we've got randomness and we've got drift.
Exactly.
And the resolvent is kind of navigating between those two forces.
Yeah, exactly.
Okay. And now they're interested in the T matrix. T sub T of Z,
Right.
which is closely related to eigenvector localization.
Yeah, that's the one we care about.
Right. And they define it as S to the 1/2 times F sub T of Z times S to the 1/2,
Right.
where F sub TZ contains the squared magnitudes of the resolvent entries.
Right. So the T matrix is basically giving us a snapshot of the resolvent,
Okay.
filtered through the variance profile S.
Okay. So it's taking that resolvent information
Uh-huh.
and kind of focusing it through the lens of the variance profile.
Exactly.
And using Ito's lemma, they derive another SDE this time for the T matrix.
Yes. So now we have another movie
Another movie.
showing us how the T matrix evolves.
Okay. So we've got a movie of the resolvent,
Yeah.
and now we've got a movie of the T matrix.
Exactly.
And this SDE, which is also presented in lemma 6, allows them to compare the T matrix
Uh-huh.
to the diffusion profile.
Ooh, sub the T.
Yes. Which represents the expected behavior of a diffusion process on a torus. Right. So we're checking if the T matrix,
Yeah.
which holds information about localization,
Uh-huh.
behaves like a diffusion process.
Right.
Which would indicate delocalization.
Exactly.
Okay. And the diffusion profile is defined as the absolute value of m of z squared times s divided by 1 minus t times the absolute value of m of z squared times s.
Right. So that's our theoretical benchmark for diffusion
Okay.
based on the variance profile S.
Got it. And by subtracting sub t from the T matrix, they define E sub t of z,
Yes.
which represents the deviation
Not deviation.
from this expected diffusion behavior.
Right.
So if E sub t of z is small,
Mm-hmm.
it suggests the T matrix is behaving like a diffusion process,
Exactly.
which points toward delocalization.
That's what we want.
That's what we want.
Okay.
And lemma 7 provides the SDE governing the evolution of E sub t of z.
Right. So now the goal is to show that this E sub t of z remains small
Okay.
throughout the time interval from 0 to 1.
So that the T matrix stays close to the diffusion profile.
Exactly. But there is a problem.
There's always a problem.
There's always a problem. This equation for E sub t of z contains these nonlinear terms, these powers of E sub c itself, and that complicates things.
So it's like the dancers are starting to improvise, go off script?
Exactly. And that makes it hard to predict what will happen.
Okay. So how do they deal with this?
So they introduce this stopping time argument.
Okay. What is that?
So imagine watching that movie.
Of E sub t of z.
Yeah, of E sub t of z evolving over time. A stopping time is like saying, pause the movie the moment E sub t of z gets too big.
Okay. So it's like setting an alarm.
Yeah, an alarm.
To alert us if E sub t of z deviates too far.
Exactly. And they define the stopping time as stop in
Okay.
equations 3.3 through 3.5. And the goal is to control the evolution up to this stopping time
Okay.
and show that it never actually reaches that critical threshold with high probability.
So it's like proving that the alarm never actually goes off.
Exactly.
That E sub t of z stays well behaved.
Right. And that's captured in Theorem 8.
Okay.
It says that the probability of the stopping time being less than 1 is incredibly small,
Okay.
vanishing as the matrix size n grows large.
So the larger the matrix, the less likely it is that the alarm will go off.
Exactly.
But how do they actually prove that?
So they construct a modified version of E sub t of z,
Okay.
denoted by E stop,
Okay.
which is essentially the same up to the stopping time.
Okay.
And then after the stopping time, its evolution is frozen.
So they're letting the movie continue,
Yeah,
but the action freezes whenever the alarm might go off.
exactly. And this prevents those troublesome nonlinear terms from causing problems
I see.
beyond the stopping time.
Okay. So they've kind of tamed those nonlinear terms.
Yes. This stopped process is much easier to analyze,
Okay.
and they show that it stays well behaved,
Uh-huh.
implying that the original E sub t of z also stays well behaved.
Up to the stopping time.
Right.
That's clever.
Yeah.
So by introducing this stopping time
Yeah.
and analyzing this modified process, they can control this potentially problematic behavior of E sub t of z.
Exactly. And this is crucial for proving their main results.
Okay, so Theorem 8 is all about controlling E sub t of z,
Yeah.
making sure it stays well behaved.
Right.
And that allows them to prove Theorem 2 and Theorem 4.
Exactly.
So what does Theorem 2 tell us again?
Theorem 2 says that with high probability, the T matrix and the diffusion profile are very close at time t equals 1.
Okay,
And this implies quantum diffusion.
okay. Now what about Theorem 4?
Theorem 4 follows from Theorem 2, and it provides a bound
Okay,
on the difference between the resolvent entries,
okay.
Gixi of z,
Uh-huh.
and the entries of a diagonal matrix,
Okay.
with m of z on the diagonal.
So it's like showing that the resolvent at the end of the movie looks very close to a diagonal matrix?
Exactly. And that suggests that the eigenvectors are spread out.
Okay, so that supports delocalization.
Yes. And this is crucial for proving corollary 5,
Okay.
which states that the density of localized eigenvectors
Uh-huh.
in the bulk of the spectrum
Okay.
is vanishingly small.
So it's like saying that those huddled together eigenvectors are incredibly rare
Right?
in the important parts of the spectrum.
Exactly.
So this further solidifies the idea of delocalization.
Yes.
Okay, so they've done all this work to show that the T matrix behaves like a diffusion process
Uh-huh.
and that the resolvent looks like a diagonal matrix.
Right.
And all of this points to delocalization.
Exactly.
But they're not done yet.
You're not done yet. We still need to make sure that the resolvent itself
Okay,
behaves as expected.
before we hit that pause button with the stopping time.
Right. We need to make sure the dancers are following the choreography before the music stops.
All right, let's dive into those details in the next part of our deep dive. So we're back and ready to tackle those final pieces of the puzzle. They need to make sure the resolvent itself is behaving as expected before they invoke that stopping time, right?
Absolutely. Can't let those resolvent entries run wild. They've got a series of lemmas here to establish those precise estimates on the resolvent entries, all building up to corollary 14.
Okay, so these lemmas are all about making sure the resolvent stays well behaved under their conditions.
Right. Remember, the resolvent is at the heart of their analysis, so they have to be really careful. Lemma 12 focuses on the off-diagonal entries, the ones away from the main diagonal.
So they're focusing on those trickier entries to control.
Exactly. What Lemma 12 says is that if you've got some initial control over both the diagonal and off-diagonal entries, you can get a stronger bound on the off-diagonal entries. And that bound is in terms of the T matrix and the variance profile S.
Okay, so they're connecting those off-diagonal entries back to the T matrix, which is really what we're interested in.
Exactly. It's all about linking things back to the localization properties. Then Lemma 13 comes in and tackles the diagonal entries.
Okay, so they're moving from off-diagonal to diagonal.
Yeah, it basically says that if you have control over the off-diagonal entries and some weaker control over the diagonal entries, you can get a stronger bound on the diagonal entries. It's kind of using what you know about the off-diagonal entries to refine your understanding of the diagonal ones.
I see, so they build upon each other. Lemma 12 gives you what you need to apply Lemma 13.
Precisely. And together they lead to corollary 14.
Okay, this sounds like a big one.
It is. Corollary 14 is what ensures the resolvent stays well behaved before they hit that stopping time. It says that on a certain event, E, where the T matrix is under control, the resolvent entries stay close to their expected values.
Okay, so their expected values being those determined by the Stieltjes transform, right?
Exactly. And all of this has to hold up to the stopping time.
So if the T matrix is following the rules, so to speak, the resolvent is likely to be in the right place too.
Precisely. This corollary, along with all those bounds on the stochastic integral and the drift term, completes the proof of Theorem 8. It's all very meticulously done.
It's really impressive how they tie everything together so carefully.
Yeah.
So they've essentially confirmed that everything behaves as expected up to that stopping time.
Right.
Now, let's zoom out a bit. They've demonstrated quantum diffusion and eigenvector delocalization under that condition WA and 811.
A significant achievement.
And it brings them closer to proving that long-standing conjecture that delocalization holds as long as W is much larger than the square root of n.
Exactly.
You mentioned earlier their approach might suggest a path toward proving the full conjecture. Can you tell us a bit more about that?
Sure. In their analysis, especially in equation 5.2, they point to a potential bottleneck in their estimates. They think a certain operator norm, which represents the interaction between the resolvent and the variance profile, might have a tighter bound.
Okay, so they've identified a step in their analysis that could potentially be improved.
Exactly. If they're right about this tighter bound, they could refine their estimates.
And potentially extend their results to that conjectured threshold of WAN12.
That's the hope.
That would be amazing. So this paper isn't just presenting a new result, it's opening up a new avenue for research too.
Absolutely. It's a really great example of how innovative thinking and really rigorous mathematical analysis can push the boundaries of what we know.
Well, that was an incredible deep dive. Our brains might need a bit of a rest after that one. Any last words of wisdom for our listeners before we sign off?
I would just say keep that equation 5.2 in mind. It's not just some technical detail. It represents an opportunity for further exploration. Imagine what could be achieved if we could refine those estimates even further.
A challenge for our mathematically inclined listeners, perhaps. Well, thank you so much for guiding us through this fascinating and complex paper. And for everyone listening, keep those brains engaged, and we'll catch you on the next deep dive. Hey everyone, and welcome back for another deep dive. Today we're taking a look at this paper called Quantum Diffusion and Delocalization in One-Dimensional Band Matrices via the flow method.
The flow method.
Yeah,
Interesting choice.
it looks like it gets into some pretty hardcore math, so
Yeah.
we're going to try to break it down for you.
Absolutely.
I'm really interested in your insights on this one because some of this stuff is a little over my head.
Happy to help. Always exciting to see how folks are applying the flow method to different problems, especially in random matrix theory.
Right. Yeah, it's always blows my mind how these like really abstract mathematical ideas can end up being so important for physics, especially quantum mechanics. I think this paper really shows that connection.
Yeah, I agree.
So why don't we just jump right into it? The abstract starts off by talking about random band matrices and how they relate to quantum systems. They're specifically looking at this type of random band matrix where the entries are Gaussian random variables, and they're trying to prove that delocalization and quantum diffusion hold true under certain assumptions. And those are kind of like two big properties that are important for understanding how quantum systems behave.
Yeah, the fact that they're using the flow method is pretty interesting. It's a powerful technique. It's been gaining a lot of traction lately in random matrix theory, and it's exciting to see it applied to this problem in particular. Oh, and they mentioned that their work improves upon previously established results, which is always a good sign.
Right. Okay, cool. So let's move on to the introduction. They start by discussing the random matrix universality class, which I think provides a framework for understanding systems where quantum states are, highly correlated.
Exactly. Think of it like systems where all the different parts are like really interconnected and influencing each other's behavior in complex ways. The Gaussian unitary ensemble, or GUE, is a classic example of a Wigner matrix, which is like a cornerstone of this universality class. And what's really cool about the GUE is that its matrix entries are independent Gaussian random variables. They follow that bell-shaped probability curve that we all know and love. And you wouldn't think it, but that simple little distribution has profound consequences for how the matrix behaves as a whole.
Right. Okay, so then they introduce the Anderson model on a lattice, which is like a fundamental model in condensed matter physics. It helps us understand how electrons move through disordered material. It involves this operator that combines the discrete Laplacian that basically describes how particles hop between sites on the lattice with this random potential. The random potential represents the disorder in the material. And the strength of this randomness, which they denote by lambda, is a really important parameter. What happens when lambda is really large?
When lambda is large, that means strong disorder, and that can actually trap or localize electrons. Imagine them getting stuck because of all the impurities in the material. The eigenvalues of the operator, those represent the allowed energy levels of the electrons. They actually end up forming a Poisson point process. So basically, they're randomly distributed, kind of like if you were to scatter points randomly on a plane. The probability of finding a point in a certain region only depends on the area of that region, not on where other points are, or even if there are other points there at all.
Huh, okay. So then what about when lambda is small?
Ah, that's where things get really interesting. For small lambda, the eigenvalue and eigenvector statistics of the Anderson operator start to look a lot like those of a random matrix, specifically from the GUE. And one of the key things about the GUE is that its eigenvectors are delocalized.
Oh, delocalization. That seems to be like a really important concept here. Can you explain what that means exactly?
Sure. Delocalization basically means that the eigenvectors of the matrix are spread out over a bunch of components. You can think of it like a wave that extends over a whole area, as opposed to being concentrated in just one little spot. So in the context of the Anderson model with weak disorder, this means that the electron wave functions are not confined to just hanging out in specific locations. They can actually spread out throughout the whole material.
Gotcha. So now we get to the heart of the paper, random band matrices, or RBM.
Yes. A random band matrix is basically a matrix where the non-zero entries are clustered around the main diagonal in a band, like if the matrix was wearing a belt.
Hmm.
The width of this band, which we call W, is a really important parameter. Now, when W is much larger than 1, and we're talking about the limit where the dimension of the matrix N is really big, the eigenvalue density of an RBM, it follows the Wigner semicircle law.
Right, the Wigner semicircle law, I've heard of that. It's like that specific probability distribution that shows up all over the place in random matrix theory. It gets its name from the fact that the graph of its density function looks like a semicircle, right?
You got it. Now, based on different theoretical frameworks and numerical simulations, there's this belief that the local eigenvalue statistics and eigenvector statistics of RBMs exhibit a kind of transition, depending on how the bandwidth WAA scales with the dimension of the matrix N.
So there's like this critical relationship between W and N that we need to keep in mind. What does that transition look like?
Okay, so it's believed that if W is way bigger than the square root of N, mathematically we write that as WAN12, then the bulk eigenvalues of the RBM, they're going to behave like the GUE. And the eigenvectors, they're going to be delocalized. But on the flip side, if WV is much smaller than the square root of n, written as WEN12, then we expect the eigenvalues to form a Poisson point process, and the eigenvectors, well, they're expected to be localized.
So wide bandwidth means delocalization, narrow bandwidth means localization. Kind of like how in the Anderson model, strong disorder leads to localization and weak disorder leads to delocalization.
You're catching on. There's actually a suspected connection between RBMs and the Anderson model. Some folks believe they behave similarly, especially when you think about the inverse of lambda, 1, being roughly proportional to the bandwidth W.
Oh, so RBMs are like this mathematical playground where we can study the localization transition in quantum systems.
Exactly. That's one way to think about it. And that's where this paper comes in. They're trying to contribute to our understanding of this transition by proving that delocalization holds for a specific type of Gaussian RBM, but only when the bandwidth meets a certain condition.
All right, let's get into the specifics then. So they're focusing on these Gaussian RBMs, right, where all the entries are Gaussian random variables. And then they also introduce this thing called a variance profile. It basically tells you how the variance of those random entries changes across the matrix. They choose a specific variance profile that makes the matrix doubly stochastic, meaning that all the rows and columns add up to 1. Pretty neat.
It is. And their goal is to prove delocalization, that property where eigenvectors are nice and spread out. To do this, they use what we call the flow method.
Okay, so how does this flow method actually work? I'm a little fuzzy on the details.
All right, so imagine you're looking at the resolvent of the RBM. The resolvent is super important in random matrix theory. The flow method, what it does is it changes the spectral parameter, usually called Z, of the resolvent. It moves it along a specific path in the complex plane. So this path, it starts at a point with a large imaginary part, and then it kind of swoops down until it reaches a point with a really small imaginary part, which we usually denote, by the way. And that I, that's crucial for studying delocalization.
Oh, so you're basically using this path to zoom in and analyze the resolvent in detail.
Exactly. Now, at the same time, the entries of the RBM, they're not just sitting still, they're actually evolving in time. We model this evolution as Brownian motion. Think of it like the random jiggling movement of particles, like dust motes dancing in a sunbeam. It's a classic example of a stochastic process, meaning the system's future depends on both its current state and these random fluctuations.
Okay, so we've got the resolvent kind of flowing along this path, and then the matrix entries randomly evolving over time. But how do they connect this to delocalization?
Good question. They introduced this thing called the T-matrix, which captures the average behavior of the squared magnitudes of the entries in the resolvent. And they compare this T-matrix to what we call a diffusion profile, denoted by theta. And that diffusion profile is actually related to the resolvent of a diffusion operator.
Hold on. So they're comparing the random matrix to a diffusion process. What's the idea behind that?
Think of it this way. The way an eigenvector spreads out over the different components of the matrix, you can kind of view that as a diffusion process. If the T-matrix ends up looking a lot like the diffusion profile, then that suggests that the eigenvectors are likely delocalized. Makes sense, right?
Yeah, I'm starting to see the picture. So they use the flow method to analyze how both the resolvent and the matrix entries change over time, and then they compare their behavior to that of a diffusion process to learn something about delocalization.
Exactly. And they find that if the bandwidth satisfies a specific condition, basically, if it's much larger than n raised to the power of 811, WAAN 811, then the T-matrix does indeed closely approximate the diffusion profile, but only for a certain range of values for the spectral parameter z.
N to the 811 power. That's super specific. Why that particular exponent?
That comes from the nitty-gritty details of their proof. It involves some pretty intricate arguments using graphical expansions, and these things called stopping time constructions. Stopping times are like setting a random alarm based on certain conditions. It lets them control the growth of error terms in their analysis. By carefully choosing these stopping times, they can make sure that those error terms stay small enough to prove that the T-matrix and the diffusion profile are approximately the same.
So it's like they're setting up guardrails to keep the evolution of the system from going off the rails.
Exactly. And once they establish this approximation, they use it to prove something called a local law for the resolvent. This local law gives us a precise estimate for what each individual entry of the resolvent matrix should be. This local law is super useful for understanding how the RBM behaves at a fine-grained level, and it ultimately leads to the proof of eigenvector delocalization.
So to sum it up, they analyze how the resolvent flows, they carefully control how the matrix entries evolve using those stopping times. They get this local law, and then, bam, they prove delocalization, all under this specific condition on the bandwidth.
You got it. It's a pretty impressive feat of mathematical maneuvering.
Now, this is where things start to get really, really technical.
Buckle it.
They start delving deep into the proof. They introduce lemma 6, which lays out a set of stochastic differential equations, or SDEs. These equations govern the evolution of the resolvent, the T-matrix, and some other important quantities.
SDEs, yep. They're basically equations that describe how systems that involve randomness change over time. Think of them like recipes for how the system evolves, taking into account both deterministic factors and, random stuff happening.
Okay, so the first SDE, it describes how the resolvent matrix, they call it xi, changes with time, which is denoted by xi. It's got terms that show how the randomly changing matrix entries influence things, the Brownian motion part, and terms for the deterministic evolution of the spectral parameter z.
Right. It's like a tug of war between randomness and determinism.
Exactly. So this equation basically tells us how the resolvent flows along that path as both the matrix entries and the spectral parameter change over time. What about the other SDE?
That one describes how the T-matrix, denoted by TTZ, changes over time. It involves terms related to the squared magnitudes of the resolvent entries and terms connected to the variance profile of the random band matrix.
So these SDEs, they capture this whole intricate dance between the resolvent, the T-matrix, that variance profile, and all the random fluctuations of the matrix entries. It's a pretty complex mathematical choreography going on here.
It is. And to really understand it, they bring in this time-dependent diffusion profile denoted by Tate. Remember, their goal is to show that the T-matrix closely approximates this diffusion profile.
Right. They want to show that the random matrix behaves kind of like a diffusion process.
Exactly. So to see how closely those two things are related, they define eats, which is just the difference between TZ and eat.
Oh, so Tates basically tells us how far off the T-matrix is from the diffusion profile at any given time.
Exactly. And the authors are trying to prove that eat stays small as the system evolves. To do that, they arrived this evolution equation for eats, which is laid out in Lemma 7. This equation, it's got terms related to the diffusion profile itself, the error term, and then, really important, a stochastic integral term. That last term captures all those pesky random fluctuations.
So it's an equation for how the error term changes over time, and it's got both deterministic and random parts. How do they even begin to control the behavior of eats, especially with all that randomness flying around?
That's where their clever use of stopping times comes in. They introduce this stopping time, stop, which basically says, hey, if the entries of eats or certain resolvent entries get too big, stop everything. Think of it like an alarm that goes off if things start to get out of hand.
So like a safety mechanism to make sure things don't get too wild.
Exactly. They then analyze the system's evolution, but only up to that stopping time. By doing this, they can control how much certain terms in the evolution equation for eat grow.
So they're like taming the wild beast of randomness by strategically hitting the pause button.
You got it. And their big result, stated in Theorem 8, is that the probability of that stopping time happening before time T1, meaning the probability of things going haywire before the evolution is supposed to end, is really, really tiny.
So basically they're saying that with very high probability, everything stays nice and well behaved and the error term doesn't explode.
Exactly. That's what they're going for. And this is a huge step because it sets the stage for proving that the T-matrix actually does closely approximate that diffusion profile, which ultimately leads to their proof of delocalization.
It's like they're building this incredibly intricate mathematical structure, carefully laying each brick, making sure everything stays balanced and stable.
It's a delicate process, and they've done a masterful job.
Well, that was quite a whirlwind tour through the first part of the paper.
We've only just scratched the surface.
I know, but I think we've laid a good foundation.
Absolutely.
We've got a lot more ground to cover, so let's take a deep breath and dive back in.
Okay. I'm ready when you are.
All right, so picking up where we left off, they're now starting to really get into the nitty-gritty of the proof. They start breaking down Lemma 6. Remember, that's the one with the stochastic differential equations, or SDEs, that govern how everything evolves over time.
Right. Those SDEs, they're the key to understanding the whole flow of the system.
Okay, so the first SDE, it describes how the resolvent matrix changes over time. They're calling it GETZ, where DEET represents time, and Z is that spectral parameter we were talking about earlier. This equation has terms for both the random part, the Brownian motion, and the deterministic part, the evolution of Z.
Yeah, it's like a recipe that tells you how the resolvent changes, taking into account both those random jiggles and the deterministic march of Z along that path in the complex plane.
Right, so basically this equation shows us how the resolvent flows along as both the matrix entries and the spectral parameter Z are changing.
It's like watching a river flow, it's constantly changing, adapting to the terrain and the currents.
Exactly. It's a beautiful analogy. Now, what about the other SDE, the one for the T-matrix?
Okay, so that one describes how TTZ evolves over time. And it involves terms that are related to the squares of those resolvent entries and other terms connected to the variance profile of the random band matrix.
So it's all about how those squared magnitudes of the resolvent entries are changing, mixed in with some influence from the variance profile.
Yeah, it's like a delicate balance between the different components of the system.
Right. It's like they're all intertwined in this intricate dance.
A mathematical ballet.
Love it. Now, to make sense of this whole dance, they introduced this time-dependent diffusion profile, denoted by n. Remember, their goal is to prove that the T-matrix ends up looking a lot like this diffusion profile.
Right, they're trying to show that the random matrix behaves similarly to a diffusion process. That's the big picture.
Exactly. Now, to measure how well the T-matrix is tracking this diffusion profile, they define EATS, which is just the difference between the two.
So basically, EATS tells us how far off the T-matrix is from the diffusion profile at any given time.
Okay, and what's the plan with this error term?
Well, they want to show that it stays small as the system evolves. They do that by deriving what we call an evolution equation for EATS, which you can find in LEM 7. It's a bit of a beast of an equation, but it basically describes how the error term changes over time, and it involves terms related to the diffusion profile itself, the error term, and importantly, a stochastic integral term. That last term is what captures all the random fluctuations that are happening.
So it's like an equation that tells us how the distance between the T-matrix and the diffusion profile is changing, taking into account all the randomness and the deterministic parts of the system.
Exactly. Now, controlling that error term, that's the tricky part. And that's where their clever use of stopping times comes into play.
Right, those stopping times. They're like safety mechanisms to keep the system from going completely off the rails.
You got it. They introduced this stopping time, stop, which basically says, stop everything if the entries of EAT or certain resolvent entries get too big. It's like setting an alarm that goes off if things start to get too wild.
I like that analogy. It's like a safety valve that releases pressure if things get too intense.
That's a good way to think about it. So by analyzing the system only up to this stopping time, they can control how much certain terms in the evolution equation for EAT can actually grow. It's like they're putting a limit on how much the error can accumulate.
So they're basically taming the randomness by strategically pausing the evolution.
That's a great way to put it. And their key result, stated in Theorem 8, is that the probability of that stopping time happening before time t1, meaning the probability that things blow up before the evolution is supposed to end, is really, really small.
So most of the time, everything stays nicely under control and the error term doesn't explode. That's a big win for them.
It is. It's a crucial step because it allows them to prove that the T-matrix does a pretty good job of approximating that diffusion profile, which ultimately leads to their proof of delocalization.
Okay, so we're at this point where they've set up this framework, they've introduced those SDEs, they've got this error term they're trying to control.
Right. They've laid out all the pieces on the board, so to speak.
Exactly. And now they need to prove that the error term stays small. That's where lemma 7 comes in.
That's the heart of their argument. Lemma 7, it's the evolution equation for the error term, EATS. It tells us how that error term changes over time, taking into account all the random fluctuations and the deterministic parts of the system.
So they're going to use this equation to show that the error stays small. How do they do that?
Well, it's a bit complex. They have to carefully analyze each term in that equation, break it down into smaller pieces, and then use various mathematical tools and techniques to estimate how big each piece can get.
It's like they're taking this complex machine apart, examining each gear and cog to make sure everything's running smoothly and nothing is about to fly off the handle.
That's a great analogy. It's really a testament to the power of these mathematical tools. They allow us to break down these incredibly complicated processes into manageable chunks and then carefully analyze each piece.
Pretty impressive stuff.
Yeah.
So what kind of tools are they using to analyze this error term? I know they mentioned these graphical expansions earlier. What are those all about?
Yes, graphical expansions. They're a super helpful way to visualize and manipulate these complex mathematical expressions. Basically, they represent each term in the equation as a graph. It's like a visual language for doing math.
So it's kind of like drawing a picture of the equation to make it easier to understand.
Exactly. And by manipulating these graphs, they can simplify the expressions and get a better handle on how big each term can get.
I'm starting to see how these visual representations can be really helpful in this kind of work. It's like taking a complex circuit diagram and turning it into a 3D model to see how everything connects and flows.
I love that analogy. It really captures the essence of what they're doing. They're using these visual tools to dissect the problem and get to the heart of how these random band matrices behave.
Now, they also mention these stopping time constructions. Can you remind me what those are all about? I'm still a bit fuzzy on that part.
Right. So stopping times are a way to control the evolution of a random process. It's like setting an alarm clock that goes off at a random time, but the time is determined by the process itself. In this case, they're using stopping times to keep the error term under control.
Okay, so it's like setting a safety limit on how much the error term is allowed to grow. And if it hits that limit, they stop the evolution and analyze what's going on.
Exactly. By using stopping times, they can make sure that the error doesn't get too big and mess up their analysis. It's a clever way to tame the randomness of the system.
I'm starting to get a better grasp of how they're approaching this problem. They're really combining a lot of different tools and techniques to tackle this challenge.
They are. It's really impressive. They're using graphical expansions to visualize and simplify those complicated expressions, stopping times to keep the error term under control, and a whole bunch of other mathematical tricks up their sleeves. It's like they're master chefs, carefully combining all these ingredients to create this delicious mathematical feast.
I love that analogy. It's really like they're crafting something special here, something that can help us understand these mysterious random band matrices and their connection to the quantum world.
Absolutely. It's a beautiful example of how mathematical ingenuity can help us unlock the secrets of the universe.
Yeah. All right, well, I think we've covered a lot of ground here in this first part. We've delved into the introduction, explored the basics of random band matrices, and started to unpack the author's approach to proving delocalization.
Yeah, we've set the stage for the main event, the proof itself.
And in part two, we'll continue to explore their work, delve deeper into those technical details, and uncover those hidden connections between random matrix theory and quantum physics.
It's going to be a wild ride. Buckle up.
I can't wait.
Me neither.
All right, so we're back, ready to dive back into this pretty intense paper.
Yeah, where'd we leave off? All right, they were just starting to break down the proof in section 3, right?
Yeah, they just introduced lemma 6 with all those stochastic differential equations, the SDEs.
Right, the equations that tell us how everything changes over time, all the randomness and the deterministic parts.
And they're going to use these equations to show that, with high probability, the T-matrix stays close to the diffusion profile, which would support the idea of delocalization.
Exactly, it's all connected.
Okay, so how do they actually go about proving that the error term, and you remember that's the difference between the T-matrix and the diffusion profile, stays small?
Well, it's a bit complicated, but they break down the problem into manageable pieces. They analyze each term in the evolution equation for each separately. It involves using a lot of different mathematical tools and tricks, including those graphical expansions we mentioned earlier.
Right, those visual representations of the equations. So they're using those to simplify things and make it easier to analyze each term.
That's the idea. They're also using stopping times to control the growth of those error terms. It's like setting a speed limit to prevent things from spiraling out of control.
I'm starting to see how all these pieces fit together.
It's a beautiful tapestry, isn't it? All these different mathematical threads woven together to create this intricate proof.
It is. It's like a mathematical symphony with all these different instruments playing in harmony.
I like that. A symphony of mathematics.
All right, so let's get back to the specifics. They've laid out those SDEs, they've got this error term they're trying to control, and they've introduced those graphical expansions and stopping times. What's the next step in their strategy?
Well, the next big hurdle is to prove a local law for the resolvent.
Oh, right, the local law. That's the thing that gives us those precise estimates for the individual entries of the resolvent matrix. It's like zooming in to get a detailed picture of how the resolvent behaves at a fine-grained level.
Precisely, and proving this local law is crucial for showing that the eigenvectors are spread out, not localized.
Okay, so how do they go about proving this local law? It sounds like a pretty challenging task.
It is. It involves a clever combination of techniques. They start by proving two lemmas, lemmas 12 and 13. These lemmas provide bounds on the off-diagonal and on-diagonal entries of the resolvent, respectively.
Hold on, just to clarify, off-diagonal entries are the ones that are not on the main diagonal of the matrix, right?
Yeah.
And the on-diagonal entries are the ones that are actually on the diagonal.
Exactly. Now here's the interesting part. The bound for those off-diagonal entries, the one in lemma 12, it relies on an assumption. It assumes that the on-diagonal entries are already bounded.
Okay, so we've got a bound for one type of entry that depends on a bound for another type of entry.
Right, and it goes the other way too. The bound for the on-diagonal entries in lemma 13 depends on the assumption that the off-diagonal entries satisfy a certain bound.
So it's like a circular dependency. They need one bound to prove the other, but they also need the other bound to prove the first one. It's a bit of a mathematical catch-22.
It is, but they have a clever way to get around it. They use what we call a continuity argument.
A continuity argument? What's that all about?
Basically, they start by observing that at the very beginning of the evolution, at time t0, the resolvent is basically just a scaled identity matrix.
So they know exactly what the resolvent looked like at the starting point.
Right. And they use that knowledge, along with those bounds from lemmas 12 and 13, to prove a local law for the resolvent for a short period of time. It's like taking a small step forward, using what they know about the starting point to establish the local law for a little bit.
It's like building a bridge, starting from solid ground and extending it out a little bit at a time.
Exactly. Now, to extend that local law to all times, they use that continuity argument I mentioned earlier. They basically argue that if the local law holds for a little bit and the resolvent changes continuously over time, then it must hold for all times. They make this argument formal in Corollary 14, which gives them a local law for the resolvent, but it depends on a condition involving the T-matrix and the variance profile matrix.
So they're using this continuity argument to connect the dots, building a bridge from those short times to all times.
Precisely. It's a beautiful example of how mathematicians use logic and reasoning to extend their results from specific cases to more general ones.
I'm really impressed with how they're piecing this whole proof together. They're starting with these seemingly simple observations, like the resolvent at time t0, and then they're using them to build this incredibly intricate argument.
It's like watching a master architect at work, carefully laying each brick, making sure everything is perfectly aligned and balanced.
I like that. A mathematical architect.
Now with the local law established, the authors are ready to tackle those big theorems.
Ah, yes. Theorems 2 and 4, the culmination of their work.
Exactly. Theorem 2 establishes the quantum diffusion phenomenon, the close connection between the T-matrix and the diffusion profile. It's like watching the eigenvectors spread out over the matrix, diffusing through it like a drop of ink in water.
And Theorem 4, that's the one that proves delocalization, right? It shows that the eigenvectors are indeed spread out and not confined to specific regions.
That's it. It's the grand finale of their mathematical symphony.
I can't wait to hear the rest of the music.
Me neither. But first, let's take a moment to appreciate how far we've come. They've introduced these complex SDEs, used clever techniques to control the error term, and now they've established this crucial local law. It's a testament to the power of mathematical reasoning and the elegance of the flow method.
It's truly amazing to see how they've pieced this whole argument together. It's like a complex puzzle, where each piece fits perfectly into the overall picture.
Absolutely. And the best part is, we're not done yet. We've still got more to explore. Are you ready to dive into the final part of this incredible paper?
I'm on the edge of my seat. Lead the way. Welcome back to the show. We're in the final stretch of our deep dive into this fascinating paper on quantum diffusion and delocalization. It's been an incredible journey through some really complex mathematical terrain.
It has. And now, in this last section, we get a glimpse into what lies beyond the horizon. The authors wrap up their rigorous mathematical arguments and shift their focus to potential refinements and open questions for future research.
Right. It's like they're saying, hey, we've come a long way, but there's still so much more to explore.
Exactly. It's that spirit of exploration that drives scientific progress.
Absolutely. Yeah. Now, one of the things they point out is that a particular estimate they used in their proof, the one for the operator norm of that expression involving the resolvent and the variance profile matrix, might not be the best possible estimate.
Yeah, they kind of hint that their bound might be a bit too loose, that a tighter estimate might be out there waiting to be discovered.
So there's room for improvement, which is always exciting. It means there are still mysteries to uncover.
Exactly. It's like they've found a path through the forest, but they're suggesting that there might be a more scenic route, one that reveals even more of the hidden beauty of the landscape.
I like that analogy. A more scenic route through the mathematical forest. Now, what makes them think that a better estimate is possible? What's the intuition behind that?
Well, they argue that their current estimate doesn't fully exploit the structure of the problem. Specifically, it doesn't take full advantage of the fact that the variance profile matrix kind of restricts the resolvent to a smaller block. It's like they're using a wide-angle lens when a zoom lens would be more effective.
Oh, I see. So their current estimate is a bit too coarse-grained, And a more refined estimate could capture the subtleties of the matrice's behavior more effectively. It's like they're looking at a pointillist painting from a distance, and they're saying, hey, if we get closer, we can see the individual dots and appreciate the full complexity of the artwork.
That's a great analogy. They're basically suggesting that a sharper tool is needed to really unlock the secrets of this mathematical structure.
And what implications could this stronger estimate have? Would it significantly change their conclusions?
Potentially, yeah. They believe that a stronger estimate could push their results on delocalization even closer to that conjectured threshold of WAN12. Remember, that threshold is like a holy grail for mathematicians working in this area. It would be a huge step forward if they could prove delocalization all the way down to that critical bandwidth.
It would be like finally reaching the summit after a long and arduous climb. A truly remarkable achievement.
It would be. And this paper lays a strong foundation for future research in that direction.
This paper has been an incredible journey. We've delved deep into the world of random band matrices, explored the fascinating phenomenon of quantum diffusion, and witnessed the power of the flow method in action.
It's been a wild ride through the mathematical landscape.
It has. And it's amazing to see how all these different pieces fit together. The random matrix theory, the diffusion processes, the intricate estimates, those clever stopping time arguments. It's a testament to the ingenuity and creativity of mathematicians and their ability to use these powerful tools to illuminate the hidden structures of the universe.
Absolutely. It's a beautiful example of how abstract mathematical ideas can have profound implications for our understanding of the physical world.
And that's what makes this field so exciting. There's always something new to discover, some new connection to uncover, some new mystery to unravel.
And who knows what amazing insights await us just around the corner.
I can't wait to find out. And to our listeners, thank you for joining us on this deep dive. We hope you've enjoyed exploring this fascinating paper with us. Keep those brains buzzing, and until next time, happy exploring. Okay, so today we're going to unpack this idea of random band matrices.
It's a fascinating area, really.
Yeah, and it gets at how complex quantum systems behave.
Exactly. You know, what's really interesting is how random band matrices can be used to model the transition between order and chaos in these systems.
Right, we've got a great paper to help us dive into this. Quantum diffusion and delocalization in one-dimensional band matrices via the flow method by Dubova and Yang.
Yeah, I think their use of the flow method in this paper is particularly interesting. It's not a common approach.
Yeah, it seems to give us a new way to visualize how these matrices behave over time.
Exactly, like watching a movie of how they evolve.
I like that, a mathematical movie. But before we get into the specifics of the paper, let's back up a bit.
Yeah.
Let's cover some basics. Wigner matrices, the Anderson model, and then, of course, random band matrices.
Sounds good.
So can you give us a quick overview of Wigner matrices? What are they and how do they relate to quantum systems?
So Wigner matrices are named after the physicist Eugene Wigner. They're Hermitian matrices, and their entries are random variables, usually drawn from a Gaussian distribution.
Okay.
And the cool thing is, even though they're random, they show universal patterns in their eigenvalues and eigenvectors. And those patterns can help us understand things like energy levels and wave functions in quantum systems.
So they give us this simplified model for looking at the statistical properties of more complex quantum systems.
Exactly.
Okay, so then how does the Anderson model fit in with all of this?
Well, the Anderson model, which comes from physicist Philip Anderson, it looks at how electrons behave in materials that are disordered.
Disordered how?
So imagine electrons hopping between atoms in a crystal lattice. But the energy levels of those atoms are random.
Okay.
And that randomness can actually trap the electrons. We call that localization.
Interesting.
The Anderson model basically gives us a way to study this localization and how it affects electron transport.
So, to recap, we've got Wigner matrices, which give us a baseline for random matrix behavior. And then we've got the Anderson model, which introduces the idea of localization caused by randomness.
Yes.
So now let's bring in random band matrices.
Oh, okay.
How do they connect to these two ideas?
They kind of bridge the gap between them.
Sure.
Imagine you start with a Wigner matrix, but then you constrain those non-zero entries to be within a certain band around the main diagonal.
Okay, so there's like a limited range where they can be.
Exactly. And the width of that band, which we call W, is what gives these matrices their name.
So you're adding this spatial constraint to the randomness.
Right.
And I'm guessing this bandwidth W is key to how the system behaves.
Absolutely. The relationship between W, the bandwidth, and n, the matrix dimension, determines whether you get delocalized eigenvectors, which are more like Wigner matrices, or localized ones, which are similar to the Anderson model.
So by tweaking the bandwidth, you can explore the transition between those two regimes.
Exactly.
And this is where Dubova and Yang's paper comes in. They really dig into this transition using this flow method.
Right. Their work provides a very rigorous mathematical way to analyze this transition.
Okay, so before we get to that, let's clarify something. The paper mentions GUE and Poisson statistics. What are those, and why are they important in the context of random band matrices?
So GUE stands for Gaussian unitary ensemble.
Okay.
It's a specific type of Wigner matrix. When the bandwidth WE is much bigger than the square root of the matrix dimension n, the eigenvalues of the random band matrix start to behave statistically like a GUE matrix.
Okay.
This means the eigenvectors are delocalized. They're spread throughout the whole matrix.
So it's like the randomness is distributed evenly throughout the system.
Exactly.
Interesting.
Now, when the bandwidth W is much smaller than the square root of n, you get a big change. The eigenvalues start to resemble a Poisson distribution, which usually describes random independent events.
Okay.
So instead of repelling each other, like in the GUE case, the eigenvalues are more scattered independent points.
Okay, so that points to localized eigenvectors.
Exactly.
Gotcha.
And this shift from GUE to Poisson statistics is a big sign of the transition from delocalization to localization in random band matrices.
So this transition, it seems like it has big implications for understanding how quantum systems behave. Like in the Anderson model, it could be like a shift from conducting to insulating behavior. Right?
Exactly. That's a great point. It mirrors that metal insulator transition in materials where how well electrons conduct depends on how disordered the material is.
Fascinating. So Dubova and Yang are focused on proving this transition, this conjecture, and they're using the flow method to do it. Can you give us a general idea of how they approach this?
Sure. They basically introduce a time parameter, and then they study how the random band matrix changes as that parameter changes.
Okay.
The flow method lets them look at the dynamics of the system, how quantities like the Green's function and the P matrix change over time.
So it's like watching the matrix evolve, seeing how its properties change.
That's a good way to think about it. And by carefully analyzing this evolution, they can connect the behavior of the random band matrix to a classical diffusion process.
Okay, that connection between the quantum world of the matrix and classical diffusion, that seems crucial to their proof. How do they make that link?
They use something called the diffusion profile, which describes how a classical diffusion process spreads out. And what's amazing is they prove that the T matrix, which captures the spread of quantum information in the matrix, can be approximated by this diffusion profile.
So in a certain regime, they're showing that the quantum behavior of the matrix is statistically similar to classical diffusion.
Exactly, and that connection is key. They can then use what we know about diffusion processes to analyze the random band matrix.
And this is where the flow method really shines, right?
Yes. By studying how the matrix evolves, they track how the T matrix changes and connect it to that diffusion profile.
Okay, before we move on to the specifics of the flow method, can you remind us what the T matrix represents? And why is its connection to the diffusion profile so important for proving delocalization?
Right, so the T matrix, we denote it by T.
Okay.
It basically quantifies how quantum information spreads out, or more precisely, the probability amplitude of an electron transitioning between sites in the system. And it's defined as
T subscript ab equals the sum over x and y of s to the 1/2 power subscript x times the magnitude of g subscript x sine squared times s to the 1/2 power subscript yb.
Yes, where S is a doubly stochastic matrix describing the variances of the entries in our random band matrix, and G is the Green's function of that matrix.
And the Green's function, just to remind us, describes how the system reacts to a localized disturbance, like a pulse of energy.
Exactly. Now, the connection to the diffusion profile, which is denoted by S, it's really profound. It's given by
the magnitude of m of z squared times s all over 1 minus the magnitude of m of z squared times s.
where m of z is the Stieltjes transform of the Wigner semicircle law, evaluated at a complex number z.
And the Stieltjes transform, if I remember correctly, it's a mathematical tool to analyze the distribution of eigenvalues.
Right. So by showing the T matrix, which is all about quantum behavior, can be approximated by this diffusion profile, which represents a classical process, they connect those two worlds. And this is so crucial for their proof because in classical diffusion, things spread out, they delocalize. Showing that quantum information spreads similarly in certain regimes supports the idea of eigenvector delocalization.
This is really remarkable. It shows those deep connections between what seem like completely separate areas of math and physics. I'm really curious to hear more about the flow method itself and how they use it to analyze the system.
That's what we'll tackle next. In the next part of our deep dive, we'll break down the mechanics of the flow method and how Dubova and Yang use it to establish that link between the T-matrix and the diffusion profile.
Okay, so let's dive into this flow method. It sounds like a really unique way to analyze these matrices.
Yeah, it's pretty ingenious, really. It connects those static matrix properties with a more dynamic evolution.
Okay.
So the main idea is to introduce a time parameter and see how the entries in the random band matrix change as this TAT changes.
So we're making the matrix come alive, in a way.
Exactly. As time goes on, the matrix transforms based on a stochastic differential equation, or SDE.
SDE.
Right. And this SDE includes Brownian motion, so there's this controlled randomness in how it evolves.
Like each entry in the matrix is getting jiggled a bit randomly.
That's a good way to picture it. And along with those matrix entries, the spectral parameter Z also changes.
Oh, right. Z, that complex number we talked about earlier with the Stieltjes transform.
Yeah.
It's involved in analyzing the eigenvalues.
Yeah, exactly. In the flow method, Z isn't fixed. It moves along a specific path in the complex plane, following a deterministic equation.
So we've got this dual evolution happening.
Right. The matrix entry is changing with some randomness and the spectral parameter changing in a very determined way. That's the core of the flow method.
I'm trying to picture it. It's like this intricate dance between the matrix and the spectral parameter.
A mathematical ballet. And the really interesting part is what happens to certain quantities as this whole system evolves.
Like the Green's function in the T-matrix?
Exactly. We watch how they change under the influence of this flow.
Trying to follow their trail as the matrix landscape shifts around them.
A great analogy. By looking closely at the SDEs that control their evolution, Dubova and Yang can learn a lot about how the system behaves. They're showing that the flow method is a powerful way to study this transition between delocalization and localization.
Okay, so let's talk about that key result of theirs, showing that the T-matrix and the diffusion profile are roughly equal. How does this flow method help them do that?
Well, the flow method allows them to link the evolution of the T-matrix directly to the behavior of a classical diffusion process.
Okay.
They analyze the SDE for the T-matrix and show that it behaves very similarly to the diffusion profile.
So they're basically watching how the T-matrix changes over time and seeing that it lines up with the diffusion profile.
Precisely. And that really reinforces their argument that in certain situations, the quantum world of that random band matrix behaves like classical diffusion.
And diffusion means spreading out, delocalizing.
Right. So this connection is crucial for their delocalization argument, showing that quantum information spreads out like in classical diffusion, strengthens their case for eigenvector delocalization.
Okay, so their proof involves controlling those random fluctuations from the SDE, right?
Right.
And analyzing the deterministic parts that guide the evolution.
Exactly. It's a pretty delicate process.
I can imagine. What are some of the specific tools they use to manage this and get the results they need?
One key technique is using stopping times.
Stopping times.
Yeah, they basically act like safety checks, preventing the solutions to the SDEs from blowing up and making sure everything stays under control.
So it's like they're setting boundaries for how the system can evolve.
A good way to think about it. And along with stopping times, they use some pretty sophisticated mathematical tools like the loop expansion and the regular vertex expansion to analyze the Green's function.
Those sound like powerful tools.
They are. The loop expansion focuses on the diagonal entries of the Green's function, breaking them down into simpler terms. The regular vertex expansion deals with the off-diagonal entries.
So they're taking this complex mathematical object and making it more manageable.
Exactly. And to help keep track of all the terms that come up, they use graphs.
Graphs, like visual representations.
Yeah, each graph represents a specific term.
Yeah.
And by studying the structure of these graphs, they can figure out the properties of those terms.
That's interesting. It's like a visual map of the map.
Exactly. And it helps them keep track of everything and make sure nothing slips through the cracks. Using all these techniques, Dubova and Yang show that the difference between the T-matrix and that diffusion profile stays small as the system evolves. It's a solid proof for their theorem, too.
It sounds like a really impressive feat of mathematical skill.
It definitely is. Their work significantly advances our understanding of random band matrices. They're providing rigorous proof for that transition between delocalization and localization, which people have been thinking about for a long time, But they do acknowledge that their result, while groundbreaking, has limitations.
Right, you mentioned earlier that their lower bound for the bandwidth, WWIP being much larger than n to the power of 811, isn't quite as tight as the conjectured threshold of a W being much larger than the square root of n. What's stopping them from hitting that tighter bound?
The main obstacle is the limitations of those expansion techniques we talked about. The loop and regular vertex expansions, while powerful, they can't capture all the finer details, especially when the bandwidth gets close to that conjectured threshold.
So it's like trying to look at something really tiny with a magnifying glass that's not quite strong enough.
Yeah, a good analogy. Dubova and Yang suggest that we might need new, more refined expansion techniques to get past that 811 barrier and reach that tighter bound.
It's a reminder that math is always evolving. There's always more to discover.
Absolutely.
Mm-hmm.
Now, going back to their proof of theorem 2, that connection between the T matrix and the diffusion profile, how do they use that to prove delocalization?
Yeah, that's what I'm really curious about.
That's where we're headed next. Their next step is to dive into the Green's function, and it all leads to their proof of eigenvector delocalization. But let's save that exploration for the final part of our deep dive.
So we've explored quantum diffusion, we've looked at the flow method, and now it's time to see how Dubova and Yang actually prove eigenvector delocalization.
Right, and this last part really focuses on the Green's function.
The Green's function keeps coming up. It's clearly a key player here.
It really is. It captures how the system responds to a little disturbance, remember?
Right, like poking the matrix and seeing what happens.
Exactly. And what Dubova and Yang do is they analyze this Green's function very carefully.
Right.
And they end up proving something they call the local law.
A local law. What does that mean?
Well, it basically says that with a very high probability, the Green's function at a specific point in the matrix, for energies within a certain range, it's going to be close to a deterministic value, a value we get from the Stieltjes transform of the Wigner semicircle law.
So even though there's randomness, the Green's function behaves predictably at a local level.
Exactly. It's like finding this hidden order within the chaos.
I like that, finding order in the chaos. So this local law, how does it help them prove delocalization?
Well, the local law is like the foundation for their whole delocalization argument. It lets them control how much the Green's function fluctuates, and that tells them a lot about the eigenvectors.
Okay, so by understanding the Green's function, they learn about the eigenvectors. But how does that lead to a proof of delocalization?
It comes down to how localization would show up in the Green's function. If an eigenvector were localized, the Green's function would have this sharp peak at a certain energy.
Ah, so localization would leave a very distinct mark on the Green's function.
Exactly. But what the local law shows is that the Green's function is smooth. There are no sharp peaks like that.
So the local law smooths things out.
Right. And that smoothness actually contradicts what we'd expect to see with localized eigenvectors.
So no localized Green's function means no localized eigenvectors.
Exactly. And that's what leads to their corollary 5, the big conclusion of their analysis.
Right.
It says that the number of eigenvectors that show any significant localization is tiny, especially as the matrix gets bigger.
So delocalization becomes the norm.
Exactly. Their proof really shows how powerful this local law is. It helps us see the structure of random band matrices and really makes a strong case for delocalization.
Wow, this whole journey through Dubova and Yang's work has been amazing.
It has.
We've covered quantum diffusion, the flow method, the local law. It's really impressive how they use all of these tools to explore the balance between randomness and order in these systems.
Definitely. Their work pushes our understanding of random band matrices forward, and it opens up new ways to think about random matrix theory in general.
Absolutely. And those insights could be relevant in so many fields, from condensed matter physics to finance. So to all our listeners out there, we really encourage you to keep exploring these ideas. Check out Dubova and Yang's paper, dig deeper, and see where your own intellectual curiosity takes you. And that brings us to the end of this deep dive. Until next time, keep exploring and happy deep diving.